Good morning, everybody, and welcome to another Rocky Mountain Ham University. My name is Willem, AC0KQ, and my co-presenter this morning, James Maxwell, is John Maxwell, sorry. Who the hell is James Maxwell? He's famous, I think. He's hiding behind the screen there trying to fix a microphone. As always, I have to remind you that RMHAM is a 501c3 corporation, and we are able to bring you events such as this, as well as support all of the other clubs that we support and provide the infrastructure that we do using donations provided by you folks out there. So if you are interested, please go to our website, www.rmham.org, and there's lots of opportunities to present, help us financially in our quest to make the world a better place. So today, what I'm going to talk about is solving problems with IPv4. And the idea essentially is that there are a lot of individual problems that we try to solve that just are very well approached by trying to track the problem down with IPv4. What we're going to do, though, is not so much a deep dive on each of the individual topics. There's probably an RMHAM University either already on the website that covers this, or something that we will present in the future on a lot of these individual topics. It's more just to whet your appetite as far as a lot of these things are concerned. If you go to our website and go to the course syllabus under RMHAM University, you'll find a lot of these things discussed in a lot greater detail. And so, just as an example, the repeater linking, how to actually set up different configurations for BPQ and things like that. There's already a 3-hour talk on that, and we'll just sort of hit that at a fairly high level and then refer you to that for some of the other things. So the question is, why in particular IPv4? Well, IPv4, I use that term because when I say IP, people think I talk about intellectual property. And what we're actually talking about is the Internet Protocol. And in particular, the Internet Protocol 4, or version 4 of the Internet Protocol, which is the one that is most widely used. So why do we actually use IP? Well, because number one, it is a universal transport, right? It is specifically designed to be extensible, and so we can build more complex protocols on top of that and fine-tune it to whatever our specific needs are. But the other very big advantage of IP is that it is very robust. So it allows us to route around failures and correct things when things break. And because it's inherently built into the protocol, it's actually very easy to design your network in such a way that it is robust against failures. And so that makes it a very unique approach to all of these specific problems. So what is IPv4 in particular? Well, there's actually 6 versions of IP that has been published. Versions 1, 2, and 3 were sort of mostly experimental. Version 4 is the packet switch network that was introduced in the early 80s and was really the first one that was used in production. And what it was used to do is to replace older switched networks, right? So before, when you wanted to connect from San Francisco to New York, it was actually a copper electrical connection all the way from one site to the other. It was a modem. Going through various individual switches, but there was actually an electrical connection. What IPv4 basically introduced is the idea of having a big fat pipe and in that pipe sending discrete quanta of information, and built into that is a piece of header information that you can use to basically throw all of those together on one end and then spread it out into individual connections when you get to the other end. And it was specifically designed to be decentralized. So instead of having to actually have one central agency that would actually administer this, you actually have much of the smarts at the edges of the network, and then in the interior of the network, you don't have to do any specific configuration. You just have a fairly low level of administration to actually get the packets from one end to the other. And as part of that design was this whole concept of robustness, where if there's a failure in any one particular link, we'll just send the traffic around some other way, and it's invisible to the people at the ends. And, you know, when this was designed, you know, the thought was, oh, there was going to be a few hundred or maybe a few thousand computers around the world that's going to use this. So we're going to actually get 4 billion addresses, which is way more than what we're ever going to need. So this will be wonderful and last, about 10 years. And so the whole IPv4 concept is still really what we use today. IPv5 was sort of a failed attempt of building quality of service into the IP protocol, and that just never really took off. And then IPv6, which is sort of the new hotness, has been defined for more than 20 years, but because of the success of IPv4 and specifically network address translation, really just has not really become the dominant network.
Yeah, I can't remember the addresses on IPv6.
Well, I can't remember them in IPv4 either, but my computer can, so that's all I need. And so the whole idea is that in IPv4, you basically have subnets, which is basically designing the network as a network of networks, or subnets as we refer to it. So as far as the things that we use to communicate, the three basic protocols that are most widely used is ICMP, which we basically use for some controls, things like letting you know that this path is dead. You can't get to the device that you want to get to. It'll send you a reply back for that. It can actually do a little bit of routing, although that's actually a terrible idea. But we mostly use it for control and debugging. For actual transport of information, we use basically two protocols, TCP and UDP. TCP stands for the Transmission Control Protocol, and actually IPv1, 2, 3, and 4 are basically different versions of IP that we use to figure out how to do TCP. And so for a while there, we actually changed the IP version number as we improved TCP. TCP in version 4 actually has enough smarts built into it that there are several iterations of how you could do TCP under version 4, and it's completely invisible to the end user. But the key thing about TCP is that it's essentially a virtual circuit. So it's a connection from A to B, and whatever you push in at the side A comes out at B and vice versa. And it's reliable, and it deals with congestion and all of those kinds of things as part of the actual protocol. So it's a great way of moving a certain chunk of information and not having to worry about all of the details of how you get it from A to B. UDP, on the other hand, is a best effort protocol, and it's very often used in things like VoIP, where you send the information, and if it doesn't arrive in time, it's probably not going to be of any use to you anyway. So the idea is that the things that we build on top of UDP, such as voice circuits, will work 99% of the time, and if there's the odd syllable that gets missed, that's just too bad. You can build reliably into that if you want to, but for the most part, we don't worry about it. We rely on the user to saying, "What did you just say?" Or "You went digital. Can you say it again?" Rather than actually building that directly into the protocol. Of course, the way that this all works is actually very well designed. So if you look at the overall OSI model, it is all based on quantized chunks of information. So there's more layers here than what really makes sense. But the way to think about this is that when you send a piece of information from one program on your computer to a remote server, what happens is that there's a high-level protocol, let's say HTTP, that the computers agree on to talk to each other. So if you send an HTTP request, which you very often use to address a device such as an APC or any kind of display of information from a power controller or anything like that, it basically has a certain header that tells the thing on the other side what it is that you want to see, right? That header says, this is the URL that I want to address that has some meaning to that device. That HTTP protocol is transmitted via TCP. How TCP works is it basically takes the actual information of HTTP and it looks for a new line character to say, this is a line of information that's going to be interpreted this way. Here's another line of information that gets sent from the sender to the receiver and then gets interpreted there. To get those TCP packets from machine A to B, we build TCP on top of IP. So IP sends discrete packets. It has a 20-byte header and then a payload. And part of that header tells it, okay, this is chunk 1 and chunk 2 and chunk 3 and chunk 4 of the actual information that you want to convey. In that process, the receiver looks at all of these discrete packets coming in, and it says, okay, I got packet 1, packet 2, now I get packet 5. Oh, what happened to 3 and 4? Hey, sender, can you send 3 and 4 again, because I just missed those? Or you get packet 1, 2, 5, and then 3 and 4. It actually reorders those so that they come out in order at the other end. So at that level, we're dealing with discrete quanta. Of course, to actually get stuff from my laptop over to the router, I'm going to either make a Wi-Fi connection or an Ethernet connection. So at that level, you basically have these discrete IP packets that now get sent over a medium such as Wi-Fi or Ethernet. Well, all that happens to all of those is that you take that discrete packet and you wrap a header and a tail around it, right? So at the Ethernet level, there's a MAC address that gets added to the front of it to tell it, okay, it needs to go from this piece of hardware here to that piece of hardware over there, and they find each other by their MAC addresses. And so basically by building all of these protocols on top of each other, you can debug and make sure that things work at the lowest level and build on top of it and make it more and more usable to the end user by just coming up with a more and more elaborate protocol. And the OSI model breaks it up into even more discrete levels, but in essence, that's how most IP protocols work. So the things that are built on IP are, of course, all of the things that we are more familiar with and use more universally, right? So DNS for name resolution is the thing that we use to translate names like www.google.com to an IP address, right? So we don't remember Google's address. Well, actually, John remembers Google's IP
it's the
address.
Internet phone book. That's the best way to explain it is the
Right.
Internet phone book.
And again, DNS is the world's most successful database because there is nobody in the world that knows all of the IP addresses. But the whole structure behind DNS is such that there's a root directory that tells you who to go ask that has all of the information. And so there's a elaborate protocol built into DNS to figure out basically any symbolic name and its appropriate IP address without anybody individually needing to know all of that. We've got the NTP protocol, which is used for time synchronization. So for example, we have pieces of hardware distributed throughout our network. And because for things like logging, it's really important that we all agree to what time it is, we need to make sure that all of the clocks on all of the devices have the exact same time. That's really important if there was a big event and you need to actually figure out what exactly happened at that event to figure out what caused the problem. You have to have all of your clocks synchronized. And NTP is the protocol that is most widely used to make sure that all of the devices agree on what time it is. HTTP, obviously, is the universal interface for web browsers. And so access to almost all of the devices that you see on the table here are over HTTP, right? It's the hypertext transfer protocol, or the secure version of it. And it's what we're going to use for the most part to actually access all of these devices, because the browser essentially becomes the universal interface. SMTP, of course, is just email. That's just the protocol that the various email servers talk to each other. Telnet is a way of basically getting a remote console. So in order to access most of the devices that we're going to access, we need to actually connect to it. And the commands that we type in is transmitted from our screen to the device and redisplayed to on device by some sort of a terminal protocol. Telnet is the original one for that, and it is largely being replaced by SSH. The problem, of course, with Telnet is that everybody in between you and the other device can see everything that goes back and forth, particularly things like passwords, which you may not want other people to see. Of course, if you have your own private network and you trust everybody on the network, that works fine. But it's probably not that great an idea to be transmitting your passwords in the clear. So what we're going to use for the most part is a protocol called SSH, which stands for Secure Shell. And SSH is basically a way of just encrypting the connection between the two endpoints, and so somebody can't eavesdrop in the middle. The other protocol that we've used very often is called SNMP. So that stands for Simple Network Management Protocol. And what it is, a machine-readable format that gives you a lot of information about the device. So for example, if you connect to a router via SNMP, you can actually get all of the information about what the ports are that are currently active, what kind of data traffic is going over it, and so forth. And it's largely used by most network management software to actually get that kind of information into a central format. However, a lot of other devices actually supports that protocol as well, and it is one of our primary ways of actually monitoring what the state of the hardware is, to actually then figure out what controls we need to send to it or what the state of it is. And the last two there are basically how we communicate by voice or by video over IP. So VoIP is sort of a catch-all phrase for any protocol that sends audio from one device to another. And to send video, there are a number of different protocols, one of which is RTSP. And I don't know what RTSP stands for. Say again? Real-time streaming protocol, which is basically a way of sending video from a device like a camera to a DVR or whatever you want to use, or your web browser in order to look at it. The key thing about all of these protocols are both based on IP. And so they basically assume that there's a way of getting from point A to point B without having to know all of the details of the underlying transport mechanism. And that's where the whole power of the design of IP comes from, that you can build all of these protocols on top of a transport layer that deals with all of the redundancy and the error checking and things that you need to do in order to deal with failures, which is really what this is all about. Similarly, there are a bunch of protocols that are built on top of SSH. So if SSH is a way of logging in from one device into the other, well, what if I don't just want to log in? What if I actually want to transfer a file? Well, SCP, Secure Copy, is basically a copy program built on top of SSH that will make a secure login and then copy files across for you. rsync is just another way of doing that, but it's much more clever. rsync in particular is very good at doing things like system updates. So if you want to copy a whole bunch of information from one site to another, and some of the information is already there, you just want to make sure that site B has the same information as site A, you can do an rsync, and it will basically look at what is on machine B, and if it's already there, it won't copy it again. So it's a very convenient way of making sure that you, for example, transfer configuration files, or as I'll show you in one of our examples later, it's how we make sure that the audio files that are generated on one machine end up on another machine without having to copy all of them, just copy over what is actually changed. SFTP is another one that's built on top of SSH, but it basically just uses the FTP protocol. But you can also essentially do a remote desktop using something like X11 by using the -X flag on SSH, which will actually then tunnel across the X connection. But really, one of the most powerful features with SSH is that you can do port forwarding with it. So, for example, I can log into a machine and say, okay, anytime I address port 2222 on machine A, forward that connection across SSH to the other machine and connect to some port on that machine, right? So if I'm, for example, in a building like this, and because this is an educational facility, there's all kinds of filters that I can't connect to some dubious sites, such as rmham.org, that I can still do that by simply forwarding, let's say, port 8080 on my local machine across my SSH connection to my machine at home, and then from my machine at home, connect to port 80, and then basically do a tunnel across that, so essentially establishing the VPN to then transport that traffic. And you can actually do it in the reverse as well. If you need to run some program on a remote machine and you want it to tunnel out to some other part or bring the display out, you can also set up a reverse tunnel. So the key thing about SSH is if you give somebody SSH access to your machine, you've basically given them access to anything on that machine, right? So obviously very convenient if you're the guy that's trying to get to things, but you kind of have to watch your...
Very dangerous if you don't know who's in there.
Right. So how do we make all of this work? Or how does the internet make all of this work? Well, there's basically two routing protocols that are commonly used. The first one is called OSPF, stands for Open Shortest Path First, and it's basically what we use on our network to make routing decisions. Essentially what you do is all of the possible connections out of a device has a weight assigned to that. That weight could mean something like bandwidth, but mostly the way that we think about it is that it is the preferred way to connect to the next device. And the lower the weight, the higher the probability that it will get used. What OSPF basically does is it looks at all of the different ways that you can get from A to B. It looks for the one that has the smallest overall cost, and that's where it sends the packets. It's a really fast protocol, so even though you may have 1,000 devices that each run this protocol, it takes perhaps a second or two to actually figure out what the path is. Once one of the links either comes up or down, it resolves the fastest path very rapidly, and then basically that's where the packets are going to go. And if you have a link failure, then that path no longer becomes viable, and it finds an alternative way, assuming that
you have an alternative way.
Right. So for that reason, it's called link state routing, right? It basically decides, is a link up or is it not up, and then decides where to send the packets based on that. The protocol that basically runs the internet is called BGP, which is the Border Gateway Protocol, if I can say that. BGP is a little bit more complex to actually set up.
And it's more picky, too.
Because it's a path vector routing. Basically, what you have is you have a table that says, this is where this traffic goes, this is where that traffic goes, and you can have, of course, alternatives built into that, but it's a lot more effort to set up, and it's basically used sort of as an exterior protocol. So at the edge of your network, you basically say, okay, this is how I'm going to steer the network to the various ISPs, whereas OSPF is typically how you use the traffic internally.
One of the problems that you have with both of the protocols is if you have a flapping link, and when I say flapping, that means a link that's going up and down on a regular basis. OSPF doesn't really penalize you for having a flapping link. All it is it changes the way that the traffic routes, and it could cause minor interruptions in the traffic. With BGP, if you have a flapping link, the BGP protocol in itself says, all right, you've flapped twice. You don't get the flap for another 7 minutes. So it shuts that connection down, hoping that it'll stabilize over that 7 minutes. So it's much more, it's a much more restrictive protocol, and it's made to run on very large connections that have a lot of traffic. And if it changes a lot, you don't want that to flap. So it tends to get very picky with bad connections.
And in particular, the problem with BGP is because it will handle such large routing tables, it could take minutes to actually resolve that, right? So that's one of the reasons why it's so picky. If you're flaky, it's going to penalize you for that. So here's basically an image of the RMHAM network. Well, you made this graph. You explain it.
So what you're looking at is you're looking at the network from north to south and east to west in Colorado. Any of the links that you see in red are in existence, and any of the routers that you see in red have an IP connection to the world. So if you'll notice, there's loops in that picture that go multiple different directions. That's where OSPF comes into. Anytime you lose a connection, it will figure out the next best connection to bring that link back up. And the north set, or the north network, the stuff that NCARC manages, there's multiple links there that go multiple directions and bring in different loops. The central part of the network has multiple loops. The western part of the network has multiple loops. So if we were to lose a microwave connection somewhere in the middle, like right now we have an icing problem at Castle Peak in Eagle, which is right at the top of the picture, sometimes that link will go down because the dish is iced. Well, what happens is everything to the west of that rides the commercial internet on that big dotted line that comes down the middle of the picture there, back to Thornton. You don't lose anything from the western side. That is the benefit of OSPF. If you look at the rest of the network, there's some green lines in there that are links that are about to get installed this summer that will build redundant paths on more places in the network to make it more stable if something happens.
So this is where IP really gives us, a big advantage over any of the more traditional methods of linking things. So for example, when we used to have linked repeaters on the Colorado connection that relied on audio paths or RF paths, then if that path is down, then you can't talk to the device at the other end, right? The main advantage of having IP is that built into IP is this whole redundancy, and it's not something that we have to add on top of the existing protocols. In fact, it's largely invisible to you, right? If you established either a TCP or a UDP connection, you just give it the address of the device on the other side, and the network has the smarts to actually figure out how to get it from A to B. And if the path that it used to use actually goes down, OSPF will figure out an alternative way of trying to get there. And so what we try to do is to design the network in such a way that it is largely consisting of loops. So if you can send traffic this way around the loop to the device, you can send it that way around the loop and hopefully get it there. So, and of course, there's lots of interconnects, so it doesn't just have to have one or two different paths. There can be multiple ways to get to the same location.
In the old days, the way we used to do this could take days to get all of the links back up, so that things, if you failed something, you wouldn't remember where all of these things are or all of the IP addresses that need to be routed appropriately. OSPF does the same thing that would take us a couple of days in our mind and sitting there trying to figure out what's wrong and what's missing in a couple of seconds. So it really has changed the stability and the robustness of our network tremendously by having a computer doing it and not Jeff Carrier in my brain.
Now, of course, there is still great ways of screwing this all up.
Oh, yeah.
The classic problem with OSPF is if you're in the old mindset of having to set static routes and you're saying, this is how you send traffic to that address, that's what essentially a static route is, OSPF will tell everybody in the network, oh, this is the way that you send traffic to that device. Send it to this guy because this guy knows how to forward it to the other end. And you're basically overriding OSPF's smarts there. So like everything, if you try hard enough, you can screw it up. The other thing that's really important in all of this is virtual private networks. So for example, John pointed out that we have a connection between Thoroton and Grand Junction so that we can get to the western part of the network in the backwards way. So that goes over commercial IP. And so what we want to be able to do is to have a tunnel where we can push packets in the one end and will pop out in Grand Junction, but it's not our network, right? If it's a commercial network, to go from Thoroton to Grand Junction, you'll probably go via Chicago.
Or Dallas.
Or Dallas. So what the virtual private network is basically a virtual circuit built on top of virtual circuits that does the encapsulation of your packets so that if you can push it in the one end, it'll do all of the translation to pop it out the other end.
We do that very heavily in our network.
The problem with that is that you've lost control over the actual circuit. So, you know, at times this may be a 20 millisecond path. At other times it could be a 200 millisecond path. And so, you know, you've got problems associated with time delays in those. But it basically encrypts the traffic as it goes from point A to point B. And as far as the network is concerned, it looks like a circuit. It's just going outside your network. And because of that, you know, if there's a fiber cut in Dallas, maybe now you next time get routed via Chicago, but there's still that robustness built into that circuit so that, you know, you don't have to worry about it. So that's largely built on existing protocols. And one of the more popular ones is called SSTP. The big advantage of SSTP is that it actually connects to port 443 on the remote device. And because port 443 is also the HTTPS port, that port is rarely blocked. Some of the other ports, some of the ISPs will actually block that port because they don't want you to run VPNs. And so one of the advantages of SSTP is that it uses that HTTPS port and is based on the same security protocol, SSL, that is used by HTTPS. So that's a popular one to use, but its performance is not quite as good as some of the other ones. So the ones that we heavily use is called OVPN, for OpenVPN. It is a fairly high performance protocol for moving, large volumes of data. And it's also fairly reliable in terms of not introducing a bunch of jitter. If you're looking more towards something that is the new hotness, WireGuard is a very popular protocol. It works very well. Support is not quite as widespread, but in the MikroTik devices, WireGuard was actually recently added was it added in later? I think it was added at the end of 6.
It actually didn't come in until 7.
Oh, it's new in
Yeah,
7.
it was
Oh,
7.
that's right, that was new in 7. So that's an alternative that you can use. However, I mean, as far as the actual use of that circuit is concerned, it's basically transparent to you. It's just a decision that you have to make when you actually have to configure your device. The last one that I mentioned is called Zero Tier. So Zero Tier is actually a commercial product. It's free for private use and what we do. And it actually has a very clever implementation that there is a distributed but central server that you can define the circuit at, and then you have all of the devices that you want on that actually connect via this secret magic key to that server, and that's how it discovers all of the other devices on your network. And so you can actually set up a virtual private network that uses these 60 character strings to find each other, and it's a good way of getting through a firewall without having to punch holes in a firewall. Did you want to add something else to Zero?
No, not really, other than Zero Tier is a really neat protocol if you're trying to do stuff out of your house and you don't want to open up ports on your firewall to do it. I use it for accessing computers inside my network no matter where I am in the world, and it's really phenomenal. I enjoy using Zero Tier. It's just, unfortunately, I would like to have it native in the MikroTik, and we're not using 7 yet, so.
Right. And it's also, you're probably familiar with the RMHAM NetLab that I've shown a number of times. That's how I access the NetLab. There's a device inside it that runs Zero Tier, tunnels out, and then I can tunnel back into the NetLab that way. So, that's sort of the broad outline of why we use IP, right? So what kind of hardware do you need to actually use that? Well, we like MikroTik hardware. Basically, the idea behind MikroTik is that it'll do anything that your high-end Cisco will do, except for 1/10 of the price. And essentially, what makes it a very useful platform is that they run a Linux kernel with some software on it that's called Router OS. And Router OS is basically just the routing part built on top of a standard Linux kernel and an interface to actually get to it. So it supports IPv4, of course, IPv6 as well, OSPF, BGP, all of the networking protocol. It's basically networking hardware, and a device like what John is showing there will do everything that the $3,000 version will do. It's just it doesn't have as many ports and it's not as fast, so you can't get as many packets through it. The nice thing about the microtics is that essentially any port can perform any function. And so in this case, you can make 4 of the ports switch ports and make one of it the port over which you connect to the rest of the internet, or you can actually make this your central router and actually have 5 different networks connected to those 5 different ports. So it makes a big difference in terms of your flexibility in terms of...
And this one has an SFP port in it, which can be used for fiber. So if you needed to connect something with fiber, which works really good at radio sites because it doesn't pass lightning. And we use it pretty heavily in locations that have high RF. These devices don't work very well in high RF environment sites like Lee Hill, which happens to have a couple of broadcast transmitters in it. It tends to mess the Ethernet up. So one of the things that we've found is that when using a device on a high power tower, we can put fiber into it and get unimpeded data flow. We still power it over Ethernet, but that doesn't hurt the data on the fiber. It's much more robust, and so far we found to be a little bit more reliable in those situations.
So as far as the devices themselves are concerned, they are extremely reliable. Of course, lightning is kind of a problem for anything, regardless of price. But it's basically was targeted at the ISP market, and many wireless ISPs actually use these devices.
Most.
The interesting thing is that what MikroTik actually does is it does not only make routers, but it also makes radios. So, for example, most of our microwave links are 5 gigahertz devices that are made by MikroTik, and one of the huge boons of using this monoculture is that the exact same operating system that runs on your router also runs on your radio. So it's not a new interface that you have to learn for every specific device. It's basically just a specialized form of each of those that run on each of these devices. So we had thought about bringing a whole stack of hardware, but I relented to just showing one picture with a bunch of different devices in it. So the black device at the top is sort of our workhorse. It's called an RB2011, and it's the router that we have at most of our sites. It has a total of 10 ports, and you can configure them as 5 switch ports for your local LAN, and then have 5 RF links, or you can have all 10 of them as different link ports. Very flexible device. Most of that box is empty. It's,
The board's only 4 inches by 8 inches. It's tiny.
Right. It's actually just the parts that are right behind those ports that is actually a circuit board. And it runs on a wide range input. It'll run at any voltage between 8 and 32 volts. So whether it's a 24 volt site or a 12 volt site, you don't have to have any special configuration for it. It screws into a standard rack. The device right below it, the white one, is sort of and what does an RB2011 cost now? About $100
$100, $102 or something. It's not
you can get them on eBay for half that price, although just make sure that the ports aren't blown out, because one of the things that we have found is when you take a lightning strike, the router will often survive, but the port will not. So that you'll just have a dead port on the router. So
And it may do unpredictable things if it's blown up.
that too. Some of these actually, I think the port 10 on that particular device I'm showing there is actually a PoE port.
It is.
You can get some of these, like the one that John just showed, actually has all PoE ports.
All 4 of these on this device have, there's 5 ports. The first one is not. It's PoE in. You can feed this over PoE, or the yellow ones are PoE out. Those can power any device from the same power that you feed the unit off of. And this plug, it says 10 to 57 volts on this. So whatever you put in, you'll get out on the PoE ports.
So very, very useful device. The white device on this image is a cloud core router. That's what we use for the real heavy lifting. So a site, for example, where you have a lot of VPN connections coming in. VPNs is actually pretty much of a CPU hog, right? Because it needs to do encryption and handle all of the different packets being distributed. So for a site like Thornton, for example, we use the cloud core routers.
There's like 120 tunnels running on that router.
So, that device, it runs the same operating system, but, you want more power, you pay more, right? So those range in price from about $500 to around $3,000 if you get the top-end device. Doug?
And for John, just showed the little small router with the PoE, and you said you put 10 to 48 volts in.
Yes.
I missed the fact, and maybe you said this, is there a DC switch converter in there such that it always puts out 24 volt
No,
PoE?
it puts out whatever voltage you put in.
So if I put in 12 volts, it's going to put 12 volts on the PoE out,
correct.
which is probably not going to power
most
most
devices will work, but they're better off at 24.
So like the radio that you have on the slide, the dish up there is a 24.
Yes,
Other
but
things
it's
are
also
48.
8 to 36 volts in. They will take either.
Yeah.
And they have enough charge pump in them to handle that.
So the bottom line is make sure that you have the right voltage for the thing
Correct.
you're powering.
So most all of the sites that we build have a 24 volt power plant, and we charge pump the 24 volts into all of the devices to ensure that we're getting a smooth 24 volts out. If we feed the router with 24 volts, it will PoE out at 24 volts. I don't recommend using your router for PoE, because if you take a lightning strike and you happen to blow up that port, well, now you've damaged more than just a port.
Commonly use that for an IP telephone. Since this is a talk about using IP for your sites, if you have an IP phone up there, that would be fine, but make sure your phone runs on 24 volts.
Yeah,
if it's a 48 volt phone, make sure you got a 48
most PoE devices
volt
are
wall wire.
48 volt PoE
Yeah.
if it's built for the IT market. And most telephones are built for the IT market. 802.3 AF, which is 48 volts on the PoE.
Yeah. I can't speak for you, but I can say I have never accidentally put 18 volts or on a 24 volt or a 48 volt. I've never done that twice in the same day.
Yeah, I can't. Mine's probably twice in the same hour. Yes.
So the last few devices on that slide is just the examples of the microwave gear that we use.
Different form factors.
The one in the lower right is called an LHG, a light head grid. It's good for a relatively short distance and in an area where it's made completely out of plastic. So, don't have cows rub up against it or anything like that. It won't survive.
The nice part about an LHG is it weighs under a pound. So if you have to hike it to the top of a mountain to put in a temporary link, it's really nice to clip to your backpack because it's not heavy.
And it's relatively inexpensive. They're about
$50.
$50 or thereabouts. The one in the middle is a QRT. That's a slightly higher power radio. It's also a 2-channel radio, so it has both horizontal and vertical in it, and it works out to better distances, about 6 miles or so?
6 to 8 miles, yeah.
And then, of course, the one that we do mostly the heavy lifting with is called a Net Metal 5. That's shown, the device is shown in the upper left-hand corner, opened up. You'll see it has a gigabit Ethernet port and an SFP cage right next to it. And then at the top end, there's either 2 or 3 SMAs where you connect the antenna. And the picture with the blue background is a 2-foot radome. And that radio is mounted at the back. And we're still looking for the bastard that put that piece of hardline across it and broke one of the links. That happens to be up at SCORE.
Yeah. Yes, that is an evidence photo.
But basically, you know, those 2-foot dishes is the backhaul that we use on most of our network. And our links vary from, a few miles up to, what is it, 56?
57.
57 miles is the longest link. So that's basically the network, right? So you need to have an IP network in order to do this. Now we get to the really interesting part of this talk, which is what can you use for it? Well, of course, in order to make sure that your network is up and around, you need to actually have some networking gear and network monitoring gear. Typically at every site, you're going to want to have a site computer so that you can actually connect things or test things locally. But now you can put in linkable repeater systems, right? So DMR, All-Star Link, Pi-Star, MMDVM, all of those kinds of things are now possible. You can also do remote bases, so you can put a remote radio, or if you want to do the built-in capabilities of software-defined radio, either for transmitting or receiving, you can do that. But in order to run all of these sites, typically you need power. And without power, these devices don't work very well. So a lot of the new capabilities that we get with IP is that we could have solar controllers and power distribution systems and uninterruptible power supplies that we can now control and remotely monitor. And you'll be surprised how often the Microsoft solution to the world's problems works. Turn it off, turn it back on again. Sometimes it just comes alive. Terrible way of solving problems, but it actually works a lot of times. So that's a wonderful thing to have. And of course, having a VoIP phone or a camera at a site makes a big difference if you don't have good cell coverage or the cell coverage is just non-existent. Having a VoIP phone at a site is, great, both a good security issue or a safety issue, but also a way that you can then call up somebody and say, hey, this is what I'm seeing from this end. What do you see from that end? And then, of course, alarms, access controls, environmental control systems, all of those things are the things that we really want to talk to about. Of course, the thing about IP is that it's actually becoming a universal protocol, right? So all of our cell phones really are IP devices, and the whole network runs on IP. If you have a Motorola radio and you need to program it, a lot of the newer protocols actually rely on IP, right? The programming software treats that phone, radio, as an IP device, and that's how it talks to it.
Even though you plugged it in on a USB cable,
Right.
it still gets an IP address, and it still programs it just like it was an IP device.
There's all kinds of very interesting applications. For example, NASA's Deep Space Network, right? It's basically an IP-based system, except that the round trip times is sometimes several minutes. So they have to have some special protocols to be able to deal with those very long delays. And of course, we're getting to the Internet of Things, where your refrigerator is IP enabled. Your faucet can be controlled remotely, and even your toilet talks IP. So what can I say? So the basics of IP is very simple, right? Every device has to have a unique address. There's only 4 billion of them, so we actually redundantly use some of those. And we use network address translation to make sure that we sort that out. Within every device, you can have multiple services running, and that are typically distinguished by using different ports, right? So you have a server, it runs a web server and a mail server. The web server connects on port 80, the mail server connects on port 25, so it's the same IP address, but the port tells you what device you want to talk to. On a local network, devices talk directly to each other by typically discovering the MAC address of the device, and they just talk directly to each other. If you want to talk to a device outside your network, because your computer doesn't know how to get to every other device in the world, we set up what's called a gateway. And the gateway basically then takes that traffic, figures out how to get it to the right place and brings your answers back. And the connection between those two are then over, whatever nebulous things needs to happen. And the term that we use somewhat uniquely in RMHAM is that we talk about each of our sites as having a subnet, and then there's actually a subnet between the two sites as well, but we refer to that as a link. And so on a link, the subnet that is associated with a link, you may have several devices, right? You have the two routers at the ends, you may have some radios and other things in between, but you want to be able to talk to all of them and check their status. So a link is just a special term for that. What is a subnet? Well, a subnet is basically just a set of addresses that we collect together, and the IP address is broken into two parts. It's called the host part that addresses the individual device, and they all share a common subnet that they can all talk to each other. And the details of that is a long story that I won't go into. The last thing that I'll mention in terms of this is the network address translation. Basically is a way of taking your device's unique address and presenting it to the outside world as if it's another device. And that translation typically happens in your router, and it's how IPv4 is lived this long, right? Typically, one public address could represent hundreds or thousands of individual machines inside a network, and the cleverness in the router takes care of presenting that to the rest of the world in a different way. So now we get to the interesting part, network devices.
You want to take a break?
But before we do that, let's take a 5-minute break, and we'll be back at
25 till.
What?
25 till.
25 till, so 9:35, and we'll actually talk about all of this cool stuff right here.
Okay. Okay, we're back.
So hope you enjoyed your break and some of the donuts. So the next part of the presentation is about, okay, what can you now do now that you have IP? So obviously the most important part of all of this is having an actual computer at the site that you can now use to connect to other devices, check connections, both analog and digital, and perhaps run some software locally, both for monitoring and control. So the picture shown there is just a generic industrial computer. Generally speaking, at these sites where you have high RF, paying a little bit more money for a well-shielded device that is tolerant of large temperature swings is a really good thing.
And it also keeps noise out of your radios.
That's true. The best thing to do is to get a radio that's actually powered by 12 volts. Having to rely on AC is not a good idea because you have inefficiencies converting to AC and then back to DC when you are actually lost power at the site. Having spinning disks at a site is a truly terrible idea. Get a SSD and get an enterprise SSD.
Don't buy cheap SSDs.
Do not buy consumer-grade cheap SSDs. They just don't last, and they fail unpredictably. So spending a little bit more money on that is a good idea. You can use Raspberry Pis at sites. They're very inexpensive, and you can get power supplies for them that'll run on anything between 8 and 56 volts. So that's what we typically use to power these. Raspberry Pis are very reliable as long as the power supply is reliable. There's nothing that eats SD cards in a Raspberry Pi better than bad power, right? So make sure that you have good power. You can also use that Raspberry Pi for control. Just remember that each of those pins on the side goes directly to the CPU. So at a site where you have a lot of RF, you're essentially attaching a bunch of antennas to your CPU, which could be very problematic. There are some really nice cases for the Raspberry Pi that are fairly well shielded that we've had very good luck with. And the other thing to worry about is heat. Most of the winter months, it's not a problem, but especially the higher powered Pis like the Pi 4 runs very hot. And if you're at high density altitude, your cooling could be a problem. So make sure that you've got either a case that touches the CPU to actually cool things down, or put one of those aftermarket chips to cool down the CPU and the memory chips. Of course, power is what it's all about, right? So uninterruptible power supplies is very useful if you need AC power at the site. So the image there is an APC rack mount unit. The image on the right-hand side is actually from a Liebert. But the nice thing about that
Which is APC now.
Really?
Yeah, Liebert bought APC.
Is that a good thing or a bad thing?
I don't know. So I want to get on the soapbox after you're done here a little bit too.
So the nice thing about that particular display is it tells you the input power to the device, what the status of the battery is, what the output power is. You can control whether you want to put it in bypass mode, whether you want it to run it on battery. You can set different logins. You can set SNMP traps that you can actually report things out to the network. And of course, when the AC power goes out at your site, the APC is probably the first thing that's going to send you an alert to let you know that there's a problem.
All right, so RMHAM has had mixed results with APCs. Pretty much everyone that we have installed in our radio sites has died. Now, we generally only use them in radio sites where there are generators, and the generator has to spin up before it will hold the computer. Generally, only the APC will hold that until it spins up. Well, they don't take very kindly to power that's not perfectly clean. So if your generator doesn't put out really clean power, the APC will start chattering. And that chattering will kill the battery, and in turn, kill the UPS. Using cheap APC UPSs or any UPS that's a cheap UPS that's not designed for computer environment, you're basically putting a gun to your head. You're going to be playing Russian roulette. It's only a matter of when the thing is going to blow up. It's going to blow up. One of the things that we've taken to doing in our high reliability sites is using a separate device, a battery stack running on a UPS that is designed for communication site environments. It's a little more expensive, but I'm warning you now, if you put UPSs in your sites, spend the money to get something that's worthwhile. The one that you're seeing right there is a 1500 rack mount, and those, you can find them on eBay anywhere from about $600 up through about $1,300 depending on batteries. And batteries is very easy to replace. 7 amp hour batteries are easy to come by. And you'll have to replace the batteries about every year to a year and a half. Just remember, this is the single point of failure in your location that you're going to have a hell of a time getting to in the winter. Yes. Any UPS at a site, any UPS, Liebert, CyberPower, APC, whatever it happens to be, you're going to hate yourself if you don't deploy a reliable high-end unit. Correct. They also don't like lightning. Correct. It's a standalone inverter. Yes. That's another thing that'll get you too. UPSs, they are an inverter. They're nothing more than an inverter. And some computers don't like the waveform that comes out if it's not pure sine wave. And there's a big difference in sine waves. If they may say it's pure, but it probably isn't. Thornton's been there, I think, 3.
We can't hear Doug back there in the back.
Is it on?
Still can't.
See if we can find another mic.
We had a failure because your microphone is not working.
He must have had some very interesting things to say, but
All I was saying, I was asking John if his use of the term APC was generic or
Brandon.
specific, and he said generic. And we've been using non-integrated battery inverter units up at our Squaw and Thornton sites for years with 0 failure. And that's the reliable way to go.
But they're designed for comm sites.
They're
rack
designed
mount
for comm
units
sites.
Designed for communication sites.
And that's what I was trying to clarify, because we all use the term an APC, whether it's APC brand or not, just because that's what we started with. But you'll find your mean time between failure is high and your reliability is less with one of these APC or UPS units that you're seeing on the screen.
We only have one left, and it's at Devil's Head, and it's a 2400 rack mount. It's about, I think it's 6 rack units, weighs about 400 pounds. It's been there for 10 years, and it's still working. but it's only a matter of time.
So when are we going to replace it?
Yes.
Well, we'll actually have a tech talk about this topic, but even within a particular brand name, like APC is American Power Conversion, is a particular company. They have consumer grade stuff
Yes.
and they have, professional stuff. And I actually had an issue with some of my computers acting up. And so I took an oscilloscope to the different devices, and some of them puts out a pure sine wave. Some of them literally put out a square wave. It is just horrendous what some of these consumer UPSs do. So buyer beware. Of course, it's always a useful thing if it has some software to actually keep an eye on things. Sorry, go ahead, Tristan.
Do you have any brands that you do recommend for self-contained UPS devices?
Well, the Lieberts used to be good, but
It's APC now. I mean, they're the same. The Lieberts are still good, but you need to get a higher end unit.
right. So for the APCs, some of the older devices tend to be better because they put out cleaner power. And I don't know whether that's just my bias or not, but some of the newer, even fairly high-end things that I've bought from APC does not put out a pure sine wave. It's a modified sine wave that is not very good, and it is less tolerant of generator input. Especially the newer devices seem to not have the filtering on the input side that it deals with noisy generator input.
A lot
as
of the
well.
commercial generators allow you to turn the sensitivity up or down on the input to
Right.
allow for that, the more swings in the variation of the power. So you might look at one of the more commercial ones, an APC rack mount or a Liebert rack mount. One of those will give you more flexibility as to what you can do with it. I've been running older APCs at my house for years, and as long as I turn the sensitivity down, they run fine on a generator. It's not an issue.
So this piece of software, sometimes I call it AP CUPSD, just because CUPS is the old print servers or
Print
Unix,
server.
but it's supposed to be APC UPSD. And whenever you buy an APC device, you get a cable like this, right? It has an RJ45 on the one end and a USB on the other end. Well, it happens to be that APC has this protocol that they can talk between their APCs and their PowerShoot shutdown software. But APC CUPSD or UPSD is basically a piece of software that you can plug many of these USBs into your computer and keep track of your APCs. So the screenshot at the bottom just shows part of what I'm running at my office, all of the different APC devices. So you can see some of those are just really small ones. They're backups, small backups devices that run individual things. And one of them is the smart UPS, which is, one of the ones that you saw in the last image. And then if you connect to that device by clicking on the actual link on the left-hand side, you get something like what is shown on the upper right-hand side, where you can actually look at things like the input voltage, output voltage, battery status, and all of those kinds of things. So a very nice utility for monitoring your devices, and it doesn't have to have the smarts in the device itself, like I showed you in the Liebert. You can actually have software running on your site computer that could keep track of all of those. And it comes with a well-shielded cable, so it's okay to use at least in a moderate RF environment. USB doesn't like a lot of RF at the wrong frequencies anyway, so
10 megahertz really tends to tear up USB.
be careful about that. Most UPSs do not let you control individual outlets. So it's basically all 6 or all 8 outlets all at once that you can turn on or off. To really be able to control devices, you need to have some sort of a power distribution unit. So APC makes one called the AP7900 that I've had some fairly good luck with. It has 8 outlets on it. And basically you plug in IP on the right-hand side there, and you can control each of the individual outlets and turn things on and off. It has a current meter that's currently showing 0 in this particular picture, so you get an idea of the total current that's going through the system. And it basically gives you a bit of a history of all of the actions that has happened. You connect to it using a browser. You can see in this case, it's actually drawing, 4.5 amps through that total circuit. The maximum power you can put through it is 16 amps. And you can actually set the load levels that it'll send you an alert if the power use goes above the lower threshold or the alarm threshold. And in that case, you can actually control individual devices. So if you have AC power devices, you can turn them off, you can turn them on, or you can pulse them. So you can actually have it set that it turns off for 30 seconds and then turn back on again to reset it. It also has the ability to stage the power up. So if you have, let's say, several computers that are going to draw a lot of current on startup, you can set it so that when the power comes on, it waits 10 seconds to turn on the first one, 20 seconds the second one, 30 seconds the next one, so that you don't have this big inrush load on your device at the beginning. So a very useful device in terms of AC power control. And you can buy them on eBay for probably $75 or so a piece. If you buy them new, they're hell of expensive.
They're $350 new.
Yeah,
You don't want to buy them new.
They're way expensive new. But there's several models in this range or this grouping. The 7900 is sort of the current
If you search
version.
eBay for APC Master Switch, you will find a selection for these. And we use these pretty much at all of our radio sites. The guys in New Mexico have blown up every one of them they've ever purchased, but we haven't. I think we've blown up one at Squaw or two.
They also use a different brand. I'm trying to remember what it
They
was.
use a Web Power Switch. Web Power Switch.
And so I don't know. I've had good luck with these APCs.
The Web Power Switches are expensive. The APCs are much more readily available on eBay and the used market. So.
Okay.
Correct. They save a lot of driving.
One real annoyance of this is it allows you one user in at a time. So if Doug logs in and forgets to log out, I can't get into the device. Fortunately, it does have a 3-minute timeout. So if there's no activity, then it does log out the last user. But you can only have one person in the device at any time. And they also support SNMP. So if you set them up correctly, your network software will keep track of what goes on and people switching things on and off. Of course, on the DC side, the RigRunner 4005i is very popular. It's a very useful little device. It's way more expensive than it should be. That's about $250 a piece. It comes in two varieties, 12 volts and 24, and you have to choose either 12 or 24. It can't be both. But the total power capacity through it is only 40 amps. So you can't run a repeater on this. However, it's really great for actually controlling things like radios and things like that don't use high power. They have two really great features. One is a soft fuse setting, so that it will actually have a soft fuse that will drop the power to an outlet if the current exceeds a certain limit, and you can just turn it back on again and reset the fuse. The other real cool feature is a low voltage disconnect. So if your site power is starting to drop, you can set it to start turning things off. So you can turn off, for example, the high current devices like your repeaters first and leave your microwave radios up so that you don't lose connectivity.
When would I
to the
use
site.
that?
Well, you tell the story.
Solar sites. we have a few solar sites out there, and for example, Mosquito Pass out of Leadville, between Leadville and Alma. That site hasn't seen sun in about 14 days.
It's like 3 slides ahead.
Is it?
Yeah.
Okay, we'll wait.
This device, in the newer iterations of the firmware, purports to support SNMP, but it is totally broken. So it's one of the things that I've yelled at the people at West Mountain Radio who makes these, and they said, well, the guy that implemented that quit, so we're kind of out of luck. You should have fired him.
Yes.
I actually did, but they haven't taken me up on that.
Willem?
Yes.
A comment from the chat. Ed K8JMW says they're using SYN-Access AC PDUs in New Mexico.
Oh, that's the one, right, thank you. So this is just a example of a couple of the configuration screens. The one on the left is the main screen, so you can kind of see the different devices there. You can label them. You can set them power to on and off, and you can see there's also a pulse button where you can actually just drop the power and bring it back. That is a good idea for connections that don't come back. On ours, there's some things that are labeled DNR, does not recover. So if you turn that off, you've just turned off your connection into the site.
You're
So
driving.
don't be doing that. Pulsing it is okay if you're very brave and you're sure it's going to come back up again after the pulsing. But the connection on the right-hand side basically deals with the things that I've just talked about. So it shows you the low voltage and high voltage disconnects. So it's basically there you set how it's going to drop the different ports when the site voltage goes down. And then there's some additional configuration, not all of which is shown in that slide, but where you can set alerts for fuses tripping, low in voltage, high voltage alerts, and all of those kinds of things. If you're using a site that you actually want to control your actual repeaters, you need to go for a little bit of a higher end device. This is the device we have at Thoroton, for example. How much are these, Doug?
700 to 800 discounted.
So, they're high-end devices. But this one, for example, has 150 amp capability through, and it's the same device for 12 and 24 volts. They're actually, well, you describe it.
Yes, on these it is 12 and 24. The rig runner has circuit breakers. These have fuses. You can see there the purple, blue, and orange fuses. I guess John's been up here because there's purple fuses. On the left, and those are 15 amp apiece. The green ones are 40 amp. There's those automotive cartridge square fuses. I think, what do they call that? A J fuse, I think. It's self-regulating to 12 or 24 because inside of this, as opposed to solid state switches, are relays. They're actually pulling a relay contact. So when you're disconnected, you're really disconnected if there's lightning on here, and very good interface you can see up there on the upper right, and you can tell it to load shed. And as John was leading into, why do we do load shedding for solar sites? But it's not only solar sites. If you have a battery bank and you have an extended outage, you do not want to draw your batteries down to 12, 11, 10 volts.
You'll kill them.
You're going to cook your batteries or kill them. And so the load shedding is on here, and the GUI is very nice. But it is 12 ports, so it's about double the cost of a 5-port rig runner. But you got more ports and I think better functionality.
So these are commercial devices. They're robust, they're well supported, but you can also roll your own. So as an example, here is what's called an SR201 relay. So basically what this has is a little PIC chip on it. It actually has built into this small IP stack. You connect to it via Ethernet, and you can send a special UDP packet to it, and it will open or close either of these relays or just pulse them, right? So it's a $20 board, $20 board that you can kind of roll your own. However, bear in mind that it's totally unshielded, so if you want to use it at a site, you probably need to add a lot of shielding to it. At $27, if you blow one of them up, it's probably not the end of the world. The other way that you can go is to use a combination of your good old Raspberry Pi and some opto-isolated relays. So what I actually did with this particular board was to run my HVAC unit. And so this is a Raspberry Pi Zero, and it read the temperature. And then this 4-relay bank, I only used 3 of those to actually switch a 3-position fan speed. And so if it gets hotter and hotter, you just set the fan to a higher and higher speed. And you can basically write your own control software to make this do whatever you want. Do not put this at a radio site, right? You've got antennas going between the relays and the boards, but there are some clever things that you can do as long as you're willing to write your own software that you can then, build relatively sophisticated control circuitry for both your HVAC and similar kind of controls as well. You can buy these commercially. Of course, there's lots of industrial controllers that does exactly this. But when you add industrial to any device, you double the price. So it's kind of one of those things where you want to decide whether you want to invest the extra money in a device that you're not going to have to worry about, or whether you want to go on the cheap, which us hams tend to be pretty guilty of, that we want to cheap out. No, it's just to hold it to the actual piece of cardboard, because this was sitting inside a fan and I didn't have a proper way of insulating it.
That's his insulation. That's high pot tested too.
Now it's your turn.
Okay, so another thing that we have is solar sites. And I don't know how many solar sites are out there and the folks that are on the call, but we have at least 2 of them. And one of the things that happens is, like the last 2 weeks for Mosquito Pass, it hasn't seen sun in a normal day. Well, you can see it here. The last few days there's a few spikes, but they're not like they normally are. The left side of that graph, this comes from our network management software, and it actually graphs the power at the site so we can tell what it's doing and we can tell what kind of solar charge we have. And right around Christmas, we didn't have enough to keep the batteries up. So we actually were getting notifications from the switch up there that the power was low and that it was dropping the repeaters. So the repeaters, the Colorado connection at this site draws about 6.5, almost 7 amps. And the DMR draws about 4. So it will drop those and it'll keep that load off the system so that the 900 mils to 1,000 mils that the 2 microwave radios and the router have stay up. There's more than enough solar up there. There's 2 kilowatts of solar at the site. But in order to ensure that we don't kill many thousands of dollars worth of batteries, we actually shed the load with we're using the 4005i there, correct? So we shed the load either automatically if we don't happen to catch it, or we'll go in and manually power them off so that they don't keep coming back on. And you'll notice that on the right-hand side of that graph, when you started to see the peaks going back up, that's when the repeaters were turned off and the actual charge of the batteries went up. That is completely done remotely. We don't have to go to the site. In fact, I don't really want to go to that site until July. But it's done over IP. It can be done automatically if you need it. Lots of functionality, very simple to get, and not very expensive. Great.
The interesting thing of this graph here is the top graph spans from December 12th till January the 9th. The bottom graph is all of last year, right? So January is on the left and December is on the right. And so if you look at this trend here, starting in about October when the sun was getting low, the total charge that we were, or the maximum voltage that we had in the system was starting to decline through the winter, and it better go back up again on the other side. But, you know,
So
you can see interesting
we have
patterns in the
3
data.
years of trend on this site. And if you look at the graph back to 3 years, you'll notice that it does this every year. We just happened to have a really large drop around Christmas because we literally had continuous snow and clouds since then. Without this kind of telemetry, you can't really tell what's going on. And you could end up spending thousands upon thousands of dollars to try to recover from something like this and not even know what happened. The Colorado Connection at this location, when they were running on their wireless links, they had no telemetry. They had no way to tell what was really going on. And temperature is graphed, power is graphed, charge current, all of that stuff, we can see it remotely. The solar controllers that we use up there, they're 80 amp, go back one slide, 80 amp Outback solar controllers, and they are connected over the internet. So we can plug an Ethernet connector into the display unit, which is shown on the left side of that picture. And it controls the FlexMax controller to allow us to actually see how much solar charge we get during a day, what kind of drain we have, pretty much everything from battery temperature to how long they think it's going to take to get to a full charge. And that, you know, it costs a few dollars on the front end, but having that data literally will save lives. It'll save Mike's life because he's the one that has to go up there to figure out what's wrong with it. Mike was at Grand Mesa yesterday. Yeah, yesterday morning or yesterday afternoon. And he had to go up to replace a microwave that's been screwing up since about November. And that's not an easy place to get to this time of the year. So
I'm still not convinced it was Mike. It was just some snowmobile dude that climbed the tower and replaced the radio. You couldn't tell who it was.
Go look at our website, rmham.org. Look at the front page. The first, there's a picture on there of Mike up on the tower at Grand Mesa. So I wanted to make sure you guys saw that we actually do stuff.
Should have taken a picture of us being stuck.
Yes.
So the other thing, of course, that's very important in terms of all of this is all of this telemetry that you get out, right? So as I've showed here, you can use the Raspberry Pi to do a lot of this. So here, for example, is a Raspberry Pi that I put a little display on. There's a wire connected to it that has at the end a device that's a Dell Semiconductor 1820 temperature sensor, and then you can connect some relays to it, right? So the key of all of this is that you can measure temperature and then change things. So where I was actually using this was in the environmental controls unit that I use at my office. But the problem with stuff like this, of course, is that it's not very tolerant of high RF environments. Oh, here it is. So a better solution to something like that is a device like this. This is actually an industrial temperature controller. It's made by this outfit called Embedded Data Systems. And basically, it has an Ethernet port that you can connect it to. And then it has 3 RJ27 style ports, but you can now connect a temperature sensor or any other one-wire connector to it. So the one-wire connectors.
Why do they call it a one wire if it has 3 wires?
Well, it's actually, sorry, I was just making sure it was not somebody waiting at the door. It's a device, it looks like a transistor, but it's this Dell Semiconductor chip that basically has a unique 64-bit ID in it. And you can power it separately, which is what the third wire is for, or you can use parasitic power. So the signals that you send to the device to actually read it can actually power it. And so you can have a ground wire and then a single control wire to actually read temperature from this device. It takes about half a second or so to actually read a temperature from it. But, as you can see, it's a very easy device to actually stick into some place where you want to measure a temperature, such as the heat sink of your power amplifier. Of course, I wouldn't recommend that you take this to a site where you have to worry about RF. A better solution for that case is something like this. Here's a nice probe. The chips cost about $1 or so, depending on where you get them. But you can get a made-up package such as this that has a nice shielded enclosure where the actual sensor sits, have a nice shielded wire, and then connect this to the actual device. And what you can do is connect as many of these in parallel as you need for as many actual individual readings that you need to take. And what you can see on the slide at the bottom is the actual output from this device, where there's a number of devices. Each of them have a unique ROM ID, which is the 64-bit identifier that identifies the particular device. It tells you the actual temperature, and then it also tells you which of these ports it's plugged into, port 1, 2, or 3. So, for identification if you really care to. And this device costs about $100. It is fairly robust in terms of RF and environmental, you can beat up on it because it's made for industrial uses. And we can then use this to actually measure temperatures, humidity, various other functionality. And this device also has a post function in it so that you can actually upload this data to a particular site where you can then further process it, put it in a database, or do whatever it is that you need to do.
Okay. So another thing that we've run into, you guys have been at radio sites and your cell phones don't work. Well, having a SIP phone is really a good idea. I know the guys in New Mexico have their own SIP server sitting down there, and they've got phones at every one of their sites. We've pretty much done the same thing up here, so that when you go out to these locations, you're not completely cut off from the world. Even though you may have a radio there, having a SIP phone makes it a lot easier because you can talk to anybody you want. There are many packages out there that give you the SIP functionality for nothing. You can build a SIP server. You can find those SIP phones, the Polycom SIP phones, which that one is an IP650 because it's not color, for about $10 on eBay.
Also, some applications you can put a
Yes.
client on your phone.
You can
and
put-
I find that's good.
I use an application on my phone called Bria, which allows you to basically get a complete SIP phone on your cell phone. There's other SIP apps out there that you can turn these things into a SIP client that works over the Wi-Fi. So if you have Wi-Fi at your radio site and your SIP client and it's talking, you'll notice it says phone ready up here at the top. It's actually talking to the server. So if I dial this number here, it says it's dialing Willem Schreuder, and his phone's about to ring. So
Hello.
that's on my SIP server, and it's fairly inexpensive to do. It's pretty much the sky's the limit. We've got them in the trailer. We've got them in radio sites. We've got them pretty much everywhere. If you have a little bit of computer knowledge and a little bit of time, there's a number of packages that are out there that can do it. We pretty much use free PBX up here. Ed James, if you've got audio, pop up and tell us what you're using in New Mexico.
Yeah, John, we're using the Grandstream phones here, and some of the models run off of 12 volts. And so that was our driving decision there. We also have, of course, is that our tech support team has one at home, so that if somebody's up at a site and needs to get a hold of us, and some of those sites don't have cell phone coverage, they can still reach us.
There you go.
I've always looked for one of these that would be red, because I've always wanted to have a red phone.
I have a
on.
can of spray paint.
Yeah, Krylon has a
fix
solution
that.
for that. Krylon has a solution.
There you go.
Most of these phones run on 48 volts.
PoE.
So you have to make sure that you have 48 volts PoE available. But there is a version that actually runs on 5 volts.
Some of the Linksys SIP phones that they have out there, if you look on eBay for Linksys SIP phones, they're actually 5-volt powered, and they work just fine on 5 volts all day long.
Yeah, and again, the ones we've chosen will run off of 12 volts or off of the PoE.
Grandstream makes a good phone. They're not too expensive. We just chose the Polycoms because somebody gave us a box of them. I think we had about 60 of the phones, so that's just what we started using. IP cameras are another thing that are a very valuable tool to us. We have some locations on mountaintops that really benefit from having IP connectivity. Do you want to go to the browser and bring up 192.168.75.97?
Right, can find my mouse. There we go.
I'm sure you know the password. Oop, wrong. So one of the interesting things about having,
You need to drag that across to the
There
other
we go.
screen because they can't see what you have.
let me get logged in so I can see what I'm typing. All right. Drop it. Come on. There's a little bit of a delay here in the display, so bear with me. This is an IP camera that is at Thornton Mountain. And what you're looking at down in the camera is the road up to the radio site, so we can see when anybody goes up there. But the nice part about this one, come on, is that it is a PTZ camera, if we can get it to take it. I don't know why it's having a hard time. There we go. That is the foothills. We could probably go over and look at Gross Reservoir for Mark Thomas, who's here. So, yeah, things tend to get a little bit of rock and rolly up there in the winter. But this is live right now from Thornton Mountain, which is west of Rocky Flats along the Front Range. And because it's a PTZ camera, you can pretty much look at anything you want. And it's really nice for trying to do diagnostics, look at fires. We were able to get some shots from some of our other cameras, and you can actually look at antennas to see if things are broken off. But finding IP cameras like this, it's fairly inexpensive anymore. This camera is about $1,800. It's a very expensive Axis camera, but you don't have to spend anywhere near that to get this quality. In the low 300s, you can get a really nice 4 megapixel PTZ outdoor camera from a company called Amcrest, which we use a lot of those. And you want to bring that back up to the presentation. It's fairly simple to install it. If you have IP at the site, you're good to go. I would highly recommend it if you have a situation where you have a remote site and you want to know what's going on, throw a camera in. It's cheap. These SV3C cameras that you see here are available on Amazon for under $50.
Yeah, they're like 30 now. Yep. The nice thing about those is they also have an infrared transmitter. You can sort of see the things around the central camera. So it works in a dark site. A place where this came in very useful was West Creek. When we had all of those break-ins there, we actually were able to have pictures of people breaking in. And it's been useful in a number of other sites where people do things that they're not supposed to be doing. The other piece that you really need to make this useful is a good digital video recorder. So what we typically use is this piece of software called Blue Iris. It just runs on any Windows machine. Unfortunately, there's not a Linux implementation of it, but the software is $60, I think?
$69.95.
And what it's particularly good at is motion detection. So what it will actually do is when it senses motion, it'll start recording. So you don't have days and days of nothing happening that you need to go through. The motion detection is a good way of then just snapshotting whenever things work.
They do have some AI plugins now for doing license plate recognition and personnel and vehicle recognition.
It also has a very nice mask. So if there's a blinking LED and it starts recording every time the LED blinks, you can actually mask out a certain part of the image and it will not record that. The only thing that it doesn't do well with is if you have a camera outside and it starts snowing, it sees motion all the time. It doesn't have a good way of recognizing, hey, it's just snowing, don't record all the time. But you know, a relatively inexpensive in addition, and it solves two great problems. One is, you know, taking pictures whenever things are happening, like people in a hang glider crashing into the side of your building. You know, if you have just the ability to see your equipment rack and see what lights are on, that is a wonderful thing. Unfortunately, most of our cabinets actually have a door that closes and locks. So having a camera doesn't help a lot, but if you actually have an open rack and you can put a camera that actually takes an image of that rack, that could save you a great deal of driving.
Is the notifications, so you can set it up to notify your cell phone on certain conditions that you want and set times when it will notify you. And I find it's really good for the Blue Iris server that I use at home.
It'll push notification to your phone. It'll send emails. It can also do FTP uploads of photos on a regular basis. Like every 5 minutes, it could send a picture of that, and you could put that on your website. It'll always send the same name. So if you wanted to be able to have a live photo like Jeff Carrier does on the Fun Machine website, we0fun.com, it has regular updated photos. I think it's every 5 minutes pushed to the website from Blue Iris. And it just adds a lot of functionality for not very much money. And that's perfect for us hams.
So the question, of course, is, well, we have all of this great stuff that talks IP, but what if your device doesn't talk IP, right? What do you do if what you have is something that only has a serial connection? So here's a couple of examples. The board on the lower left is called by a company called WizNet. It's basically a little module that has an IP connection on the one side and RS-232 output on the other side, and you can convert IP signals to basically RS-232 signals. You would telnet into this device, and everything that you would have sent over the serial connection then gets sent back and forth to that Ethernet connection. You also, there's this signaling.
This is a Silex here. This device it's called a Silex DS510. And what it allows you to do is take the two USB ports on here and pass them to any computer with a driver, just like it was hooked up directly. So you could put a radio programming cable in one of these, bring up your radio programming software at home. As long as you're on the same network, you could program that radio on this device at the remote location. really saves a lot of driving. And this unit is, trying to remember exactly, this is like $140, 140 or 150. I think I found this one on eBay. It's called a DS510. And I think I bought this for $60 a couple of years ago. But they make wireless versions of this so that you don't have to plug it in on Ethernet. It runs on only 5 volts, so that is a bit of a limit. You'd have to have a step down from 12 to 5. But the functionality that you get from this is just like having a PC at the local site and not having to have the hardware there.
And of course, you can get varieties of these, like this Digiport that's shown up there, the port server, that will do 4 serial ports. So you can actually control 4 devices, especially if you've got some legacy hardware that only supports RS-232.
Digi makes a single port, a 2-port, and a 4-port version of that. I've been able to find the single port version, which is called a port server TS1, on eBay for $25 each. And they're generally wide input voltage, 8 to 36 volts. They work really well for programming radios, managing console ports on SCOM controllers, things like that.
Speaking of which, Dave, do you have a mic? Do you want to describe what this slide does? So let me just rag on him. So SCOM still doesn't make a controller that is IP enabled. It's all just this old serial stuff.
Yeah,
But
what you're looking at here is the serial port on a 7330, an SCOM 7330 controller. I've added a number of features in the firmware that allow you to remotely manage it. If you're logged into, for example, a Linux box, you can use Minicom. And these are screenshots of Minicom running on a Linux server. The upper left display and well, mostly the upper left display has a remote front panel. How often do you want to see the LEDs on the front of the box up there? You could use one of those IP cameras and point it at the front, or this will show you the same thing as well as some additional information like what supply voltage is being supplied to the controller, or what the voltage is on a battery stack. You can also do firmware updates remotely if you're brave. The lower right corner in that screenshot shows the transfer protocols. In Minicom, you have to add an optional LRZSZ package, and that enables you to have X modem, Y modem, and Z modem. And the 7330 uses X modem for binary transfers between the controller and the system.
So there's CRC there too. So you don't, with X
They are.
modem, you have CRC. So if it got corrupted, it would kind of be able to figure it out.
Exactly.
so, of course, there's multiple ways that you can do this. One is to actually have a site computer. And as Dave just described, you're actually logged into the site computer, and then you connect to the 7330. You could also use one of those
Port server.
port servers, and then have the connection between your laptop where the actual terminal program works and the remote device be IP, and then have the, it's just a translation of IP into serial at the remote end.
Is that the reason there's so many bright blue lights? That you could also use the camera, right, to look at these?
Well, the bright blue lights is just to keep the room lit. Of course, the other thing that you could do is, let's say you have a KPC3 and you want to talk to that KPC3. This is an example of the KPC I have sitting on the hilltop behind my house, that I have one of those WizNet ports plugged into, and I simply telnet to it, and I type at the terminal like I would if I were directly serially attached, and you can, do whatever you want to do as far as those things are concerned, as if you're locally to the site. Do we want to take a break now before we talk to repeater linking, or should we just keep going?
How many slides you got? Can you tell?
No, it's not that many more. Let's just talk about repeater
Keep going.
linking. So, of course, one of the other nice things about IP is that it allows us to actually link various repeaters together. So many of the digital modes like DMR, D-Star, and so forth, because they are digital modes in the first place, are designed to be linking various repeaters together. Of course, if you're on the analog side, we have All-Star, IRLP, Echolink, and there's probably a few others that allow us to use regular analog repeaters with appropriate hardware to then link things together. Almost all of these uses the UDP protocol to actually do the connection between the different repeaters. But because UDP is a best effort protocol, you really need to make sure that your network is as reliable as it can be. There's really two big issues that makes the audio sound terrible. The one is latency. So if there is a long delay between when the receiver hears it and when it actually gets to the other site, gets processed and perhaps gets sent back, you unkey and you hear the last 2 seconds of your transmission. This is very annoying, especially if you have an annoying voice like me. And you have problems with people doubling and it's nice to have a fast turnaround. So having a low latency network is good. The other problem is jitter. So what's worse than having a long time delay is a time delay that varies all over the place, right? And we call that jitter. That sometimes it takes 20 milliseconds, sometimes it takes 200 milliseconds, and the software on both ends just doesn't deal with that very well.
If it can't predict what the delay is, it gets confused.
And in particular, P25 is really sensitive to those delays. Things like All-Star, we can tolerate, around 100 milliseconds without too much of a problem. With P25, if there is a jitter that goes from 30 to 50 milliseconds, it causes problems. And so, especially if you have P25 connections, you really, really have to worry about it. So how do you do this? Well, first of all, All-Star is sort of the original. So the device that John is holding in his left hand is the URIX. That was really the first device that became commonly available to use this All-Star link methodology for linking repeaters. Go to the other one.
I got to go this way.
The device on the left-hand side there basically has a DB25 port on the one side that has audio and control signals, and it has USB on the other side. And essentially what's inside is the CM119 chip, which is a USB audio chip. And it will basically send audio or receive audio from the analog side and turn it into a USB signal that you can then feed.
It's a sound card.
It's a sound card. That's exactly what it is. And so this is the original. I think you can still buy them. They're about $75. But there's been a few people that actually built a better mousetrap. So if we go back to the slide, the one in the top right-hand side is the one that's built by Repeater Builder. The ones on the bottom are also, the lower right is the Repeater Builder. The left one is Masters Communications, I think.
Masters is the lower left.
So we actually have some examples here of these devices. So what John's holding is an example of a 16-pin connector that fits on the back of a Motorola radio. So there's two of them that are tied together. The one goes to the transmitter, the one goes to the receiver, and it has a micro USB connection, or actually that's a mini USB connection.
Yeah, it's mini.
That you feed to the radio, and you can use two mobile radios and a computer, and you can build yourself an All-Star node out of those. So it's a fairly straightforward mechanical and electric setup, and the software is quite robust and mature, and setting up an all-star link repeater is a fairly straightforward process. And this is essentially the technology that CRA uses at most of their sites. They have a proper repeater, not a couple of mobiles like this
But
shows.
using this.
But has a URI-X that then connects to a modem, and that is how many of the CRA repeaters are tied together. The alternative to using a standalone computer with one of these USB connections is called the RTCM. So this is a picture of the RTCM. John is holding a physical example in his hand there. And essentially, this is PIC-based, basically a type of microcontroller that has an Ethernet stack and some minimal software that will take in the analog signals from your repeater, digitize them, and then forward them to an all-star node. In order to do this, there's two things that are required. The first is, of course, that you need to know what time each of those packets are actually received. And then if you tie multiple of these together, you can actually set up a voting system. So by comparing the actual signals that come into all of the different receivers, you can time sync them and decide on which one is the strongest signal and then rebroadcast that. Each of these devices can then also act as the transmitter site. So in the configuration, you can tell it whether it should take the return signal and then actually put that back out to the repeater so that you can then control the repeater, key it up, and then send the signal that it needs to broadcast out that particular port. In order to synchronize things, there's also a GPS required so that you can get accurate timing, and that goes into that DB, what is that?
So 15.
DB15 connector. And so, the pinouts on all of those are, peculiar to these particular devices. Really popular, we use these at most of our sites, but the person that used to make these went through some troubled times. So these are they still available? Or they are again available, right? So you can buy them again, but the Colorado Connection actually has plans to get the 2.0 version of this going that integrates much better with MTR 2000 and MTR 3000 repeaters. And if you'll remember Doug's tech talk from 2 weeks ago now, sort of went into that topic into some detail.
It's on the website if you want to look at it.
Is it on the website?
Yeah.
Okay, and this is Doug on the mic. I'm off camera, but just a quick comment on this. Willem has a very nice second bullet. GPS timing for voting. The voting works very well. He says, and simulcast. So if you're like me, I looked at that and said, wow, simulcast. Caveat emptor, let the buyer beware. This really doesn't simulcast properly because to simulcast, you have to have everything locked, and the free-running crystal oscillator in this thing is not locked. So it really doesn't simulcast. But we are going to be doing what we're calling Voter 2K. It's a joint project with Colorado Connection, RMHAM, CRA, ARA, Northern Colorado clubs. We're all getting together, and we're going to do a version of this that works well with the Motorola repeater line. This module, Willem pointed out in a previous slide, be careful what you're directly connecting to your processor or your PIC or your whatever. This is exactly what they did here. There's no buffering. When Dave at SCOM looks at this thing, he hides under his desk in the fetal position because it's so bad. and he's going to do a better design on his, and he's working with our project. We will have a new version for 2000. Hopefully it will simulcast properly because we'll lock the clocks. If you're interested in this and you've got to move immediately, buy some of these. They're available. But if you're not in a hurry, join us on the project and get some of the new modules that will be better.
I did put simulcast in double quotes, right? So the nice thing about this particular module is this, along with the repeater, is the only thing that you need at your site, right? So the actual node controller can be at a remote site. So for example, at the Winter Park site, we have a repeater, we have one of these devices, and the actual controller, the asterisk node, is at Thornton. However, think about what needs to happen in order for that to work, right? The packet needs to go from this device all the way to Thornton and back to this device, and then it gets retransmitted. So if you think about a local repeater, if it's a second to the remote site and a second back, that adds a 2-second delay between when the repeater gets the signal and when it gets rebroadcast, right? So that's one of the things that you need to be concerned about. The other thing is that when it comes to voting, it doesn't like it when you have a lot of packet loss, right? So you want to make sure that you've got a very reliable connection between all of your voters and the site at which the voting occurs, which all happens in software, but you have to have a machine that actually handles that. So one of the solutions that we've actually implemented at some sites, Durango being one example, Akron being another, is that you have one of these devices and a Raspberry Pi at the same site. So the signal gets sent from this device to the Raspberry Pi, and if it needs to repeat, it gets sent right back. The Raspberry Pi then acts as a standalone node, which we then can connect to another node. And the node-to-node connections are much more tolerant of latency and jitter than when you have to send it from the RTCM to a remote node and back. Of course, that means that your RTCM needs to be reliable. So that means good power and good shielding, right? So, you know, Raspberry Pis are wonderful, but they are not industrial devices. So do what you can to baby them, to make them behave well. However, the key thing in all of this is that you now have the ability to see a great deal of detail of what's happening on your network, right? So here's a slide that shows the Colorado connection, all of the repeaters that are linked together, and it shows in green where that transmitted signal is coming from, right? And of course, all of the other repeaters that are connected here are rebroadcasting that signal. So if you have noise coming into the system, this helps you identify exactly where that noise comes from because it's the one that's lit up. It's the one that's receiving that signal. So you can troubleshoot where problems occur in the network by just looking at the screen to actually see where things come from. If you're interested in the voting part, here's another screen from the same interface where it actually shows you the signal strength coming in from all of the different receivers. So the bars here are different colors that show you how All-Star is seeing that particular link. So if it's a blue bar, it is a potential receiver that it could use. If it's a green bar, it's the one that it's actually using to retransmit. So you can see this signal is not very good. This happens to be James talking on the Colorado connection, James Isaac. And so he doesn't have a very good signal into some of the southern repeaters, but he has a fairly decent signal into Thornton, at least at this particular instance in time that I took the shot. And so basically these bars move in real time, showing you the signal strength of all of these different receivers. This Allmon is basically a piece of software that we generally use together with All-Star to basically monitor the system. It can also be used to control. So you can use this to connect or disconnect various receivers, reconfigure the system and so forth. Although to really get into the meat of reconfiguring the network, the All-Star system, you have to go and edit some text files, which Mark is good at. But of course, this particular display is an instantaneous display. What's really useful is to use this other piece of software we have that's called Allfall, right? So it's basically the All-Star Link waterfall, right? And what it shows you is all of these different receivers, but it's time history. And so in this particular case, what we see there is that there was a transmission that lasted 4 seconds, and then there was 5 seconds of space, and then there was, another transmission that lasted 10 seconds or so, another transmission from that same repeater, and then you see there are some blue pound signs that show up that now came from, what is that, Colorado Springs? I can't read that.
Yeah,
sorry.
that's Colorado Springs.
And so basically it shows you the activity that has occurred on the repeater over time. So you can actually, if you're interested in looking at a short history here, see how the signal varied over time. What this display does is it works over a web interface. So you connect to a central web server to actually see this display. And so it just turns the number between 0 and 255 into a number between 0 and 9. And if it's full scale, it shows a pound instead of a numerical value. But it gives you an idea of what the signal strength is at different times. And basically what we're using here is we're using our IP network to actually go out to each of those repeaters. There's a part of the node software that is the management interface that you can connect to and say, give me the signal strength for all of these various devices, and both the Allfall and the Allmon software is what basically gets that information to you to then store. We can also record the audio on our repeaters. So here's an example of the Allfall playback. So it shows you the exact same display in terms of signal strength that we had before, but now it shows you at the bottom that you can go and listen to the actual audio. So basically built into Asterisk is the ability to record all of the audio. And so all we do is we say, archive all of the audio that you get into the repeater, and then synchronize that with the signal strength so that we can actually see not only where that was received, but we can listen to it. So I actually have a little demo here for you from the AriesNet last Sunday. So
Right. Put it on the right screen.
whoops, sorry, I'm on the wrong screen. So here is the signal strength, and down here is the actual audio. And the delay is driving me crazy.
This is W0BNC. My name is Bob, and I represent Region 1, District 1. I will be next control this evening.
Right, so you can actually see,
Sunday evening at 8 p.m. on the Colorado Connection repeater system, the 525 Alpha.
you can actually see the signal strength that came into that particular set of receivers and then listen to the audio. And if you want to look here, so if you look at this particular transmission here, you'll notice that that signal strength was not as good. And if you listen to it, so that was the live that I showed you before. That was James checking in. And you can see, oh yeah, he's not being received quite as well. But we can listen to the audio and say, well, you know, his signal strength isn't that great. But you can still hear him very well. So this is very useful for being able to troubleshoot any issues that we have on the repeater, as well as just, if there's something happening on the repeater that you may want to have a permanent record for. Here you can see where that was actually received and have a copy of that audio available for whatever purposes we need to put it to. So very useful tools that we can now have because we now have a digital system for linking all of these repeaters together. As part of that Allmon program, we can also, of course, link in various other connections. So you'll actually see there in the middle, there's a transmission that Amanda made from a system that was linked into the Colorado connection at that time. So we don't have signal strength recorded for that, but we have a recording of Amanda saying, "Hi, it's Amanda. I've got traffic for the net." So, the All-Star method of linking these analog repeaters together gave us a lot of capabilities that we didn't have before. Of course, if you're more interested in the digital side, Pi-Star is a very popular piece of software that runs on a Raspberry Pi and gives you all of these digital modes. So here is an example of an interface card that's made by Zimmerman. What's Zimmerman's first name? Scott Zimmerman of Repeater Builder. It basically has USB in, actually Ethernet in through a Raspberry Pi, and then this board is a daughter board on the Raspberry Pi that you can then connect to whatever kind of device you want. So this particular pair is the kind that plugs into your Motorola mobile. It also makes a card that plugs directly into an SCOM controller. There's a version that you can connect directly to other repeaters. But so basically, it has all of the hardware here necessary to generate digital signals. And then what Pi-Star allows us to do is to configure the software that actually drives that. So you can use this both to run a hotspot, and Mike, K0NGA, basically had it was a tech talk on how to build a Pi-Star node from the ground up. That's on our website that you can go and look at as to how you want to do this. If you're interested in mostly building a hotspot, or if you're interested in actually putting up a digital repeater, this particular hardware allows you to do that as well. And Jeff, K0JSC, actually runs some of these multi-mode repeaters in this way. And it supports a whole bunch of different modes. Additional to DMR, it'll do P25, Fusion, D-Star, NXDN, probably does others that I can't think of right now. But the actual configuration through this web interface makes life, well, the web interface isn't all that intuitive, so it's not a walk in the park, but it's a lot easier than messing with text files. So go take a look at Mike's talk if you're interested in doing that. Of course, because these are all digital modes, they are built for connecting repeaters together, right? And so All-Star and all of these other modes have the ability to actually designate repeaters by nodes, and you just connect them together, and you've got a network, computer network. You want to talk about DMR?
Another thing that's near and dear to RMHAM's heart is DMR. We chose DMR over many of the other protocols out there because it gives us significantly less complexity at the radio sites with a device that is off the shelf. Basically, it takes power, antenna, and Ethernet, and these systems can basically connect together. It will give you the ability natively to connect up to 15 repeaters. Well, if last count, I think we had 40 on our website. you'll notice that's a little bit of a problem. To talk to more than 16, we had to purchase another piece of hardware, which is actually software in our case, from a company called Rayfield. I believe that, who's the guys that are remarketing that, Doug?
John's looking at me here. Both Rayfield and
Bridgecom, that's it.
sell a version of the C Bridge that's by another company.
It's still the same. It's written by a company called TLNet.
Yeah. Think of it kind of like a Linux kernel, and they put their shells around it.
It's basically a device that allows you to connect multiple repeaters together in multiple locations and route traffic accordingly. We chose to do that because it gives us a lot more functionality with what we can put in our network in different locations. Like certain repeaters may carry Rocky Mountain wide and central. Certain repeaters may carry Rocky Mountain wide and eastern, like our VHF network. In order to be able to make this work in software, you need to be able to route that traffic around. And we use the C Bridge, which in our case is a virtual piece of software running on a server at Thornton Mountain. And that's kind of the hub of our network. That gives us the ability to also see what's happening around the network. Can you go full screen on this, Dave? It's really hard to see
Hey,
small.
John, you once described this to me very simply. You said, think of this as a router for IP Site
Yes.
Connect. And it all made sense to me. When you have an IP Site Connect that you had on the previous screen of 16 repeaters, they all have to be identical.
Correct.
With a C Bridge, you can break them apart.
So if you'll notice here, in each of these lines on this picture, the first line is RMHAM Northern, and it's showing El Dorado, Akron, and Cheyenne. We're missing something there.
I stole the slide from an old presentation.
Oh, okay, okay. Yeah. Well, wait a minute, is something broken? The next line down is Central, and that is Thornton, Squaw, Badger, Breck, Vale, and Mosquito. I think there's actually like 10 repeaters on the Central network right now. But at any one point in time, if you're on Rocky Mountain wide, in this case, it's showing that the signal is coming in from Methodist on the Southern network, and it's routing to all of the other repeaters that are showing red. Every one of these individual lines on here is a separate master. That master is a grouping of repeaters that in our case is mostly geographic. So the northern repeaters are all in the northern section. Draw a line from Boulder across to the east, and pretty much everything north of that line is northern. Everything south of that line is central. And if you go down to right about, the easiest way to explain it is Monument Hill. If you drew a line across Monument Hill, east-west, that's going to be everything southern south of that, including New Mexico. So because these are geographic, and there is a talk group, Rocky Mountain wide, that goes to all of these, the C Bridge takes that traffic and injects it into each of the masters separately to give a seamless representation of Rocky Mountain wide. Even though there's a whole bunch of individual networks, the C Bridge takes the same traffic destined for wide and puts it in all of those repeaters. It is, as Doug said, it's a router for IP Site Connect packets. You can do this without a C Bridge, but a network that is as complex as ours, and the fact that we have stuff going a bunch of different places and we've got different networks in different places, we needed to be able to break it up because we didn't want all of that traffic on the whole network. That's where this came from.
And the reason why this works so well with IP is, of course, digital radio simply takes your analog signal, converts it into discrete packets, and then that's what gets sent between the sites, right? So in the digital voice domain, all that IP does is add a wrapper around that audio packet and gets it to where it needs to be unwraps the packet or the wrapper around it, and then delivers it to the remote machine. So there's a very good match between IP and all of this digital technologies. Of course, the other thing that you get with these Motorola repeaters is something called RDAC. So you can actually remotely access the repeaters and mess up the configuration to your heart's content.
You can change channels, you can set power levels, you can turn the repeater off, you can reboot the repeater. That's essentially all you can do with RDAC. But what it does do is give you the ability to look at incoming signals and voltages and some diagnostics for the repeater. So the functionality that's there with the Motorola platform is really good.
At a price.
At a price. It's a little hard to get them right now, too.
The other thing that's nice about the C-Bridge, it gives us lots and lots of diagnostics. So this eye chart here just shows a bunch of traffic that was, hey, this is your slide. A bunch of traffic going through the C-Bridge, and it shows you not individual packets, but individual transmissions. It gives you the ID that came out of the radio that identifies it, tells you where it came from, and so forth. So
it gives you a bit error rate. It gives you a signal strength, tells you what talk group you're on, tells you what radio ID it was, tells you what repeater you came from, and what talk group you're supposed to be on. We can supposed to be. And with all of you folks running Chinese radios out there, the ever-changing firmware makes it kind of a moving target. Nothing really ever sticks. If I went to the C-Bridge at any hour of the day, I can pretty much see a traffic that says, what does it say, undefined?
No, that's a corner case, and I just fixed that. When John said, oh, the Northern Network only has, I just went to the C-Bridge, it is accurate. But as I'm sitting on the C-Bridge here, I said, I saw the talk group undefined, and I realized that there are two users that are on the wrong time slot with the wrong talk group.
Right.
And I just detected that, and I'm getting ready to send them a very nice nastygram because they're nice people that are usually in this room, but they got their programming wrong of their cheap Chinese radios. We need to send them to Mike's class.
One of the things that we see
and they're on the wrong time
talk
slot.
group
That's how we detect
undefined
it.
a lot. And this software allows us to be able to manage what you as an end user is doing out there. And we can tell that somebody didn't spend enough time with the code plug to make sure that you're on the right time slot and the right talk group. We're not going to yell at you for it, but you're not going to talk to anybody. So just be aware. When you're not talking to anybody and you keep yelling into the radio, you know somebody's supposed to be there. You might want to go back and find another code plug on our website and stick it into your radio.
And
I
for
would just
John's
like to point
benefit,
out-
we were not properly coding Boulder Local. So it was coming up as talk group undefined. I just fixed that. But the Boulder Local guys were on the Eastern time slot. That will come up undefined, and that's how we detect.
Correct.
I would just like to point out that the cheap Chinese guys don't have a monopoly on programming the radios wrong.
No, they don't.
So, of course, the other thing that IP allows us to do is to have remote access to devices like software-defined radios. Again, just another category of digital radio where we can use devices that takes RF and turns it into another signal. Most of these turn out to be USB-based. So the three examples I have up there is an RTL SDR, which is basically an RTL 8020 chip, which was developed for European broadcast TV, but is widely used as a receiver for SDR radios. The one in the top right-hand corner is the SDR Play. Is that a Duo?
That's a Duo.
Which is both HF and VHF, and of course, the Cadillac is the HEC RF1, which is a very high quality device for taking RF signals in, and they all go USB out. So when you have a device like this, You can, of course, deploy it at a remote site. Depending on the particular device, it can act as a receiver or a receiver and a transmitter. And then you have to get the signals out. So you have two choices there. One is to basically take the stream out of this device as what's called an IQ stream in the digital signal processing world. It's basically just all of the information from the analog world converted into a digital stream in a way that is convenient for processing. The other thing that you could do is at the local site, actually process those IQ signals into just audio and then just bring audio from the site to wherever you are. Doing the audio processing on site has the big advantage that you're using audio bandwidth to bring back to where you actually are, right? Which is a 40 kilohertz signal or a 40 megabit per second signal gives you a very good audio quality. Some of these devices will sample 20 megahertz of spectrum, but you have to bring that 20 megahertz of spectrum down to your actual site for processing, right? So you can actually saturate your link, especially if you have something like a HEC-RF1, which will generate a tremendous amount of data that you then need to move to your local site where you do the processing. How you actually do that processing is very much a function of what you're trying to do. So RTL SDR is a piece of software that's very commonly used in things like Direwolf for packet decoding, where you can actually just process a narrow band of the signals and then turn it either into audio or packet. OpenWebRX is a very neat web-based interface, which I'll show you an example of here in just a second, where it's basically an image that you burn to your Raspberry Pi. You connect one of these devices to it, and you can actually listen to the world there. But again, if you want to roll your own and you want to be able to do essentially anything in the world, GNU Radio is a very cool software package that gives you lots of modules and a cool interface to actually tie all of these together and actually build a radio. If you're interested, we've had a couple of RMHAM universities about software-defined radio that shows you how you can build a receiver, both digital and analog, as well as a transmitter to actually then process that. So again, look at the website. There's some really cool stuff as far as that is concerned. But this gives you the ability to put a receiver at a remote site, and if an individual user says, your repeater sounds kind of wonky today, you can actually go and listen to what that remote signal sounds like by using one of these remote receivers. WebRX is a really cool program that I just referred to. Here's an example of some of the output from it. And in particular, what it shows is a waterfall display. There's all kinds of controls over here and over there. But in particular, I was listening to 14531 Thoroden here, and you can see there was actually a transmission there. There's the RMHAM 145175 on Squad DMR that just completely blows everything away at my house. And I think this is 14514, no, this is one, I don't remember what, I think that's probably 145145. Also a signal that's really well heard at my house. This is just a Pi and an SDR play that's sitting on my desk. I can actually show you a live demo of that, assuming somebody is actually on the system at this time. Oops, sorry.
Just go to 145, 145. Somebody's always there.
Did I close this? Oh, there it is. I cannot read that screen. And the delay is killing me. Let me grab it and bring it back to my screen here so I can set it up.
Yeah, the delay is a little frustrating. I think Dave is going to do a Nerd Fest. Is that next month? Or is, yeah. we're going to do a Nerd Fest next month on how all this stuff works here. And there is a lot of smoke and mirrors that goes into being able to make this work.
So right now, there's no signals being received, so you just hear the squelch. But
There is a squelch pot.
well, yeah, but just switch off the radio. So essentially, this is just a live demo of everything it's receiving. You can see most of those lines are just, birdies more than anything else. But there's controls down on the right-hand side where you can set the modes that you want to receive. Depending on the particular device you have different. Oh, there's the DMR just came on. Whoops, what did you do?
I pushed a button and made it freak out.
This delay is driving me crazy. And I was going to try and listen to that transmission. If you click on it, it should change. Oh, it was the 145, 145. Dave, can you get one of your friends to talk? Actually,
I just heard it go
Yeah.
beep.
Somebody just kerchunked it. But you can basically get about a 600 kilohertz snap of the band and basically see anything. This limitation is on the actual device that I have connected to it. If you use something like the HEC-RF, you can get a much wider spectrum all at once. And of course, you're also to some extent limited by the processing power of the Raspberry Pi to just decode all of those signals. You can see there was a DMR receiver actually, a signal being received. In order to decode DMR, you need an AMBI chip. So there's actually an add-on module to OpenWebRX where you can plug one of those DV3000 modules into the Raspberry Pi. It'll send the signal to the AMBI chip, decode it, and then send you back the audio so you can actually listen to, oh, there's, Tristan has an example of one of those, to actually be able to listen to all of the audio that comes out of the device. I had hoped that we'd do this earlier so we could listen to the connection, the preparedness net,
You
but they're
didn't talk
long
fast
gone.
enough.
Well, that's your fault.
That's the AMBI chip. It's basically in a little plastic USB kind of container. And that gives you the ability to decode. Is this one capable of doing P25 and DMR, or is this just the DMR?
I'm actually not sure if that will do the full rate codecs. I think there might need to be a slightly different model number, but it will definitely do DMR.
And D-Star,
Yeah.
which all happen to be the same codec, but slightly different implementations. Good little unit if you're trying to do digital modes on your Raspberry Pi with OpenWebRX or any of the web receiver systems. He needs a mic.
Going to say there's also an IP version of that codec as well, which has got a ESP32 processor on it, Ethernet port, USB, so it just has more interface.
Basically the same thing,
but not
instead
USB,
of USB, it's Ethernet.
It's Ethernet, yeah.
Right.
And it's about the same price too. They're about $150.
I think those were 100 if I'm not mistaken. Yeah.
Right. So, I mean, the bottom line is if you're interested into getting into software-defined receivers, especially remote software-defined receivers, OpenWebRX is by far the easiest way to go. And if you want to know more details, we have an RMHAM University on that.
Imagine that. We keep saying
Matthews
that.
gave one last year that went through all of the details of how to do all of this. So again, another great capability that IP adds to us. Of course, something that's very popular with people like David Dean is a remote base. Inside joke. So you can basically remotely control your receiver or transceiver. This is very popular with people who are on HF remote bases. So the lower right-hand corner is a device called remote rig? Yes,
That's the remote rig, yeah.
it basically has a transmitter and receiver box. The receiver connects to your transceiver. The transmitter controls to your local device, and you have a microphone and a key and speakers and so forth that allows you to remotely control a device that, like a radio, that was not necessarily designed to do that. MFJ makes a Raspberry Pi based version of the same thing, much lower cost, but it's based on a Raspberry Pi, so reliability is not quite as good, although, what did David Dean use? Was it a Raspberry Pi based one?
I'm not sure.
Oh. So the key with all of these things are that, as long as you have an IP connection, of course, you can basically be anywhere in the world and operate that radio. And of course, if you have one of the latest and greatest radios from Elecraft or ICOM, the radio now actually has that ability built in.
Just add this to make sure that you can turn it off.
Yes. So the other thing that you can do with remote bases is you can actually set up an all-star node as a remote base. So the GPIO pins in the Raspberry Pi can be used to steer the channels on a radio, such as
They have the, what is this thing? This is the DMK engineering.
Right.
The USB radio interface, they call it a URI. It has basically GPIO logic outputs on it that you can steer a radio. We had remote bases working with Motorola CDM series mobiles, and you can steer 16 channels in any bank with that. As long as you select the bank, from software in the Raspberry Pi and a pull down, you can choose which bits get twiddled and actually change the channel on the radio. It's very nice. It's a very nice implementation. It makes it really nice for remote radios.
Of course, the other very useful thing is remote APRS receivers or transceivers and weather stations. So here's just a collection of different devices that you can use as an iGate. So the one in the lower right-hand corner is called the WX 3-in-1. It's about $150 or so.
$130.
It was originally designed as just an APRS device, but they've actually added the capability that you can connect a weather station to it. It'll give you temperature.
Can connect temperature sensors to them also, one wire.
And so basically what that has is an Ethernet port, and then the backside of that device has a port that you can connect any radio to, and then basically set up an iGate. And of course, all of the received APRS packets then gets forwarded to one of the APRS IS sites like aprs.fi, and you can basically use the web to track the location of various APRS sites. If you want to roll your own, the lower left-hand side shows Raspberry Pi with TNCX or TNC Pi daughter board on it. So that daughter board is the one that actually creates the tones that you can then use to decode signals from your radio or encode, say, signals if you want to. Or if you want an all-in-one unit, the one in the top right-hand corner is made by the same person as does the W3-in-1, but that actually contains a 7-watt radio in the same box. And so that box contains the Raspberry Pi, as you can tell on the left-hand side, that does the iGating, but he also has a, what's that little transceiver module, I forget the name now. That's basically a low-power VHF or UHF transmitter that you can connect. All you need is a IP connection, power, and an antenna to actually have a complete iGate unit.
There's also a presentation on BPQ and iGate on the website from previous RMHAM universities.
Needless to say. One other interesting thing, speaking of BPQ, is that we actually have, you can use BPQ, not only BPQ, but other packet software as a way to provide WinLink radio RMS. What is an RMS?
Radio message server.
Radio message server. So the idea is that you can use the WinLink program to actually connect via packet to one of these devices. And when that device is actually connected to the internet in general, you can send email via packet by basically connecting to one of these RMSs, and then that gets forwarded to either another RMS or to the central message server, CMS, which is basically a worldwide system, right? So you've all probably heard of WinLink. Well, basically, if you have IP at your site, you can set up an RMS by simply providing that interface between the RF world and the IP world. And so this particular image is from the BPQ station that I run for the traffic league. It's called K0NTS. It's a BBS. That BBS you can connect to by RF. But if you also want to forward traffic from there to the WinLink system, you just add RMS : in front of the call sign, and it'll actually send it via RMS. This also has another piece of interesting software that's called NTS Gateway. And basically, if you look at your WinLink software, you can send a radiogram, and instead of sending it via RF, you can send it to the WinLink system and designate what region this traffic needs to go to, and it will get sent to this generic IP address or email address that lives on the WinLink system. So what the NTS Gateway software does is, because this particular BPQ node is connected via the RMHAM backbone to the internet, it'll actually go to WinLink, read the traffic that's destined for the NTS system, download it, reformat it so that it is compatible with the NTS digital system, and then drop it into this BPQ node, which then is part of the NTS digital system, and it'll transfer via RF these different messages to wherever it's sent to. It's typically routed on the zip code, but so if you have a zip code at NTS Utah or NTS Wyoming or NTS Maine for that matter, it'll figure out how to send that particular message via RF to the appropriate station, and obviously it needs to be delivered at the other side by becoming part of the NTS system. The key thing then again though is, as long as you have IP at your site, there's software like BPQ that you can use as an interface between all of the different packet modes that we have, VARA, traditional packet, backtor, and so forth, and then get connected to the rest of the world via IP. You can also tie some of these BPQ nodes together. There's a protocol called AXIP, which is basically the AX25 protocol, which is what we use for packet, that's encapsulated in an IP packet, and then these BPQ nodes can talk to each other, forward messages, or you can hop from one node to the other to actually then connect between all of these sites. Of course, the other thing that IP is very, very useful for is connecting various receivers together for direction finding. You want to talk about the DDF?
So DF is something that's gotten pretty near and dear to our heart here in Denver because we've got some bad actors out there that they know who they are, and we do too. We've spent a lot of money and time. In this case, we've purchased Doppler systems, DDF 7000s, which are internet interconnectable receiver units that actually do full Doppler. So what you can do is you can put one of these things in a fixed location. You can put one of these in a mobile location. And all of the data necessary to track a signal is transmitted in packets to an application called Target Track. And you see a picture down in the lower left here from Target Track. And what it has done is it's taken 3 mobiles and plotted a location and given me a circle on the map that says your interfering transmitter is inside this circle. We have these here in Denver, hence my comment, we know who you are. This technology it's not inexpensive and it's very time consuming, but it's very solid. And it gives us the ability to find things that you don't think is possible. Well, think again.
And again, you know, what IP gives you is, first of all, the ability to tie all of these Doppler units together. So if you look at the picture here, you'll see it has an Ethernet port over which it will then transmit all of the signals that it measures locally. These just shows an example of a mobile and a static installation that it uses to actually receive the signals. And then this particular image here shows all of the different connected units where it actually plots it. And what IP gives you is not only the ability to find all of these pieces of information, but it gives you the ability to draw maps, right? And real-time maps where you can see actually addresses, and as you drive around, see where you are, where the target is, and so forth. So again, a tremendously a good enabling technology. And of course, you can integrate this with what I've shown you before from all-fall and the playback, where you can actually say, hey, did you just hear that? You can go back and listen to the signal from a few seconds ago and see the signal strength from all of the static receivers and so forth. So again, a wonderful enabling technology to allow us to do lots of other things. So in the last few minutes here, just want to talk a little bit about network management tools. So the key thing with any technology like this is unless you actually keep on top of it, it's very easy to get away from you. So you need to have good network management tools to make sure that your system is up and running when you need it. So the tool we happen to use is called Observium. It is a network management software, or actually NMS is kind of the technology that it generally uses. This is just an image from the main screen where it shows you all of the green dots are the location of all of the sites that are currently up. If the site is colored red, there is some device at a particular site that's misbehaving in some way. And it gives you a tremendous amount of information about the number of devices that are up, any events that it sees, logging of events such as that the signal, you know, the connection dropped or anything like that that shows you what's going on. So this is an example where we're actually looking at a particular port on a particular router. It shows you the traffic that's going through that router. You can have a short view of just the last 24 hours. You have a view that goes back a week, a month, and a year. So you can see trends in the data. You can see when there was sudden changes to the network, where suddenly your ping times went from 20 milliseconds to 200 milliseconds. Well, what just happened? Clearly there was something in the routing change. Let's go see what went on. And you can get a tremendous amount of information about all of the things in the device that is being reported. Most of this is pulled out by SNMP, so your device has to be SNMP capable. But all of the MikroTiks that we use gives us pretty much almost all of the information that we would like.
Most of.
The other thing that's very nice about this is you can get alerts. So this happens to be an alert that I got that the APC at Castle Peak lost power. And so you can integrate these alerts with either email systems. This happens to be a screenshot of Telegram. Mostly what you want is alerts on things like power outs. You can set it to alert that if a port goes down because the device on the other side failed, or maybe just the plug fell out, or a rat ate through it. Those are all good alerts to get. One of the problems that we have with the networks, such as OSPF, which is self-healing, is it's the third or the fourth failure that you may notice, right? So you need to pay attention to your system alerts, because it'll tell you the first and the second failure that you can go fix, so that you don't actually lose the network on the third or the fourth or whatever failure. But you do want to have adjustable sensitivity on these alerts. There's nothing more annoying than your phone just dinging and dinging and dinging, and it's just nuisance alerts. Observium allows us to actually set certain timeouts on it, and the motto of our network operations is DFIU, don't mess it up. The hallmark of a good operator is that when you do DFIU, that you fix the problem before Observium alerts.
15 minutes.
Which is about 15 minutes. So not that I've ever done it, but for example, you could have a device sitting on the bench, and you think you're in it, and you reset the configuration, but you just went and looked at another device just to see what the configuration was, and you forgot to change back to this device when you reset the configuration, and then bad things happen. But I've never done that. The other tool that we use is called smoke ping. Basically, this is from the CRA smoke ping. It shows you the time to different devices. So this happens to be El Dorado, West Creek, in the APC. And it just tests whether it can ping it and how long the pings take and how many are lost. If you zoom in a little bit more detail, you can actually see at a smaller time scale of about 3 hours, it actually saves more detail. And why the reason these are called smoke ping, these are called smoke graphs, right? So the gray area shows you the variation in the ping time. So if it's very wide, there's a lot of variation in the pings, so a lot of jitter. The green shows you the average. And then the color of those lines vary depending on how many packets were lost. So the fact that this all shows green shows that all of the packets actually got replied to, but you can see that there is some jitter in the signal. And you can look back over time, basically the last day, 30 hours, the last week or so, 10 days, and then the last year. And you can kind of see, there was a time here when something happened in the network, and the times were quite a bit different than they were before. So we want to keep track of that. Smoke ping basically sends you a packet or a test every 5 minutes. So it gives you
20 packets every 5.
20, sorry, but it's all 20 packets all at the same time, right? So it basically gives you a snapshot of the network every 5 minutes. The tool that we use to look at it at a smaller time scale.
Holy moly.
Yeah, that didn't come out very well.
That's jitter.
Well, that's a smoke ping. CPing. And what CPing actually does is down here is all the devices, and then going across is the ping times on a 1 second interval. And so this is a very good way of looking at problems with jitter on the network locally. So the color of the character that it draws tells you whether it's measuring in milliseconds, tens of milliseconds, hundreds of milliseconds, or if it's red, it actually lost the packet. And so you can see in this, over the width here, which is about 2 minutes, how the actual ping times varied in short duration. You can also see that there was a 3-second outage where from that router onwards, none of the packets actually came through. So this is a good way of keeping track of a link that just drops for a few seconds and then the network heals itself. So it's a good way of getting close to real-time status of what the network is. But basically, you know, it gives you a view of, let's say, the last hour on the network. So it's not a long-term record. And this is actually a program, it's just a C program that we typically run at a few sites, so you can see what the network looks like from that particular site and give you a good idea of the jitter in the algorithm. And we actually have a very interesting article on the RMHAM website where we discovered a problem with router OS that it was introducing a lot of jitter in a particular version of router OS. And how we discovered it was just looking at these graphs and then looking at how those ping times changed over time. Excuse me.
You talk too much.
My voice gave out right at the right slide.
Yes.
So, you know, I hope what we've conveyed today was that having IP at your site gives you the ability to do a whole bunch of stuff that otherwise you wouldn't have. It gives you the ability to not only connect sites together, the repeaters, but it also gives you a lot of telemetry that you can then use to take corrective action before it becomes a real problem. And all of this telemetry, we have great software for that we can, you know, record over time and look at the trends and make sure that if there's a break in the trend, that we can troubleshoot what the problem is and take corrective action before, excuse me, it becomes a problem. You finish, I lost my voice.
Okay. I think the most important thing that you should learn out of this is if you have a network that you want to be reliable, use the tools at your fingertips and make sure that you're taking advantage of all of the new technology out there to try to manage and monitor what you've got. Next month, we've got NerdFest. Have we got any signups for NerdFest yet?
I haven't posted it.
Okay. Willem is going to post all of the stuff for NerdFest this weekend. If you guys have a presentation you'd like to do, you don't necessarily have to be here. You can be remote. We can get you in for the presentation, no issue. It's basically, I think it's a half hour, and 10 minutes of that half hour is questions, correct?
Right.
So it's a very short presentation. We're going to look to do, I believe, 6 of them. And it's a time for you to get something that's near and dear to your heart out into the open, shed some light on projects that you're doing. The sky's the limit. You can be as nerdy as you possibly want to be. I know that none of us are nerdy at all, so I think I know of one presentation, which is how we're doing these productions. Dave is going to do that. We believe that some of that's going to have to be recorded because it's really hard for us to do a production and show you how the production works. So it may not, yeah, it's a little bit of a cart before the horse there. But if you guys have interest in it, great. As always, RMHAM is a 501c3. We're a charity. If you see fit to have a very soft spot in your heart for us, donations are always gladly taken. See Wayne Heinen, N0POH, who's here in the room. And we look forward to seeing you next time. If there's any questions, yeah, you can go to our website at rmham.org.
And there are tons of buttons.
Yep, lots of buttons to be able to pay, or I think there's a why donate.
We have Why Donate. It'll give you some information about us. We also have PayPal. We have a pledge program. We have donations through Colorado Gives. And we also have a snail mail address where you can mail a check. So
And cash. Cash is always
Cash,
good too.
like
Find
cash,
us.
too.
We love it.
there you go.
Thank you very much. Look forward to seeing everybody
Hey,
next
John,
month.
John,
Swap
just,
this.
just to be clear, NerdFest is Saturday, and it will be live here.
Yeah.
And also broadcast.
Yep.
And then after Saturday, we'll head up to the Swap
Fairgrounds.
Fest for setup.
Correct.
And the Swap Fest will be Sunday,
Correct.
and you don't want to miss that, right, Wayne?
That's correct.
Two things on the same
Wait,
weekend.
That is the Saturday before the,
Nerdfest is Saturday. Swap Fest is Sunday.
oh, okay. That'll
Yep.
be the 18th for the Nerd Fest.
Yeah.
19th, Adams County Fairgrounds for the Swap Fest, so. come
Tickets
up
are
and see us.
available for the Swap Fest on
We have-
rmham.org.
We have plenty of tables available still. We're about half sold out. And we're doing $6 for admission this year. Sorry, Adams County wanted some more money. Tables in advance, $13. Tables at the door, $20 if we have any left. So we'll see you on the 18th. We'll see you on the 19th.
Thank you guys for attending.
Thank you for being here.